right, hello everyone. Welcome to my FPGA development live stream today. My name is Alex Ferencic. I am a postdoctoral researcher at UC San Diego. So I do a lot of work with FPGAs for networking applications, and that's what we're going to look at today. Now, before I get into the material, I have a couple of quick announcements that I want to make. Right, so the first one is that I recently set up a Patreon account. So if you like what I do and you want to show some support, you can go over there and support me. The link should be in the description. And for the FPGA fanatics out there that want to see this stuff in real time, if you will, I'm planning on doing some kind of unscheduled, unscripted kind of live streams on just whatever I happen to be working on at the moment. So if that's something that interests you, support me on Patreon, and I'm going to make that available to people that support me at any level. So the next announcement is that at some point I am thinking about doing kind of a more in-depth porting live stream. So previously I did a couple of streams porting to some of the Xilinx boards, and those were primarily in terms of, it's a new board, so we just need to change the pin assignments and whatnot, and then everything will just work. But in this case, what I want to do is port to not just a new board, but a new FPGA series, most likely using this board, which is one of the Microsoft Catapult FPGA boards, and going through the entire process. So that is, bringing up the PCI Express interface, making the model of the hardcore in CocoaTBX PCIe, modifying the PCI Express DMA engine to talk to that, bringing up the Ethernet interfaces, and then making the whole thing work. So that's definitely going to be kind of a multi-part sort of thing. I'll do that at some point. I don't know exactly when, but at some point I want to do that. So if that sounds interesting to anybody, one advantage of these particular boards is that they tend to be available on eBay for relatively cheap. So that's a good thing. But the problem is that these do require a cordless license in order to target. So if you just want to listen in, you probably don't need any of that. But if you wanted to, say, follow along at home or something, you might need to find a way to get access to a cordless license somehow. I don't have a solution for that now, but maybe we can figure something out if there's some people interested in that. Right, and then the last announcement is that I'm going to be having, at some point in the next couple of weeks, basically a developer meeting for Corundum. So we're thinking about potentially rebuilding some portions of Corundum to support RDMA. And as part of that, we would need some help from the community. So if you're interested in using RDMA on Corundum, or just using Corundum, or if you might want to help work on Corundum, join the mailing list. The link is right at the top of the README in the Corundum repository. So go take a look at that and hop on the mailing list if that sounds interesting. I'll be posting more information on the list. Again, not exactly sure when that's going to happen, but it'll be relatively soon. All right. So now for the content for today. What I'm going to be working on today is porting the verilog-ethernet design to run on a couple of different Intel FPGA boards. So I've gotten quite a bit of support from both Intel and Xilinx in terms of getting Corundum up and running. Xilinx has donated a whole bunch of Alveo boards, and recently we requested a couple of boards from Intel. So what we're going to do today is basically do kind of an unboxing on a couple of these dev boards from Intel, and then I'm going to go through and I'm going to bring up the QSFP interfaces at 10 gigabits per second, and we can go take a look at what's involved in getting those serializers working on the Intel FPGAs. And not only that, also some of the debugging tools that are available. Now, before I get into this, let me talk for just a couple of minutes on, on selecting FPGAs, right? If you're going to be working on a project that needs FPGAs, Obviously, the specifications of the FPGAs and their capabilities are an important consideration, but there are other factors that need to be considered. And one of them that I've seen before, at least if you're doing academic research type stuff and you might be getting grants, some of those grants will come with various strings attached. I think one of them that I saw a while ago, I think Intel was one of the sponsors, and one of the conditions is that you had to use Intel FPGAs. So you might have external considerations for why you might want to use a particular vendor or brand over another one that really have nothing to do with the technical capabilities or technical considerations. That's one aspect. Another aspect would be maybe ecosystem considerations, right? If you have a big code base that uses Intel IP cores or Intel QSys, or maybe the Xilinx IPI flow, the block diagram flow, that can be very hard to port to a different tool chain. So that might drive the selection of a particular tool chain or a particular series of FPGAs over another, just based on kind of legacy considerations. Or maybe you really like OpenCL and Intel's OpenCL support is better than Xilinx, or whatever. Another consideration is going to be board level stuff, right? If you want particular capabilities on an FPGA, at least for a lot of stuff that's done these days, you're probably not going to be making your own board, at least for these big FPGAs. You're probably going to be buying an off-the-shelf board. So maybe you can only get boards with the capabilities that you want that have Intel FPGAs on them, for example. And that might drive your decision. And then finally, you have the capabilities of the actual FPGAs, right? How many logic resources, what sort of clock you can run it at, what the serializer capabilities are, what sort of memory interfaces they support, things like that. So that was one of the considerations as well with this. The Intel devices here, at least with the Stratix 10, they supported PCIe Gen 4 by 16 before Xilinx. I think right now, like only maybe the Versal parts support Gen 4 by 16, and those parts aren't even widely available. So anyway, so today we're going to take a look at two different Intel development boards for Stratix 10 DX parts. We got a for Stratix 10 parts, we've got a Stratix 10 DX FPGA board, and then we also have a Stratix 10 MX FPGA board. So let's take a look at what you get with one of these things. See if I can go out a little bit with this. Right, so there we go. This is the standard Intel Stratix 10 DX FPGA development kit. We'll just start with the unboxing section here real quick before we get into the actual coding and getting this stuff operational. All right, so inside we got two boxes. Let's see what we got. This one is very heavy. We got a bunch of power cords, including, well, have you ever heard the term power brick? That's about the size and about the weight of a brick. Let's see, what are the ratings on this thing? Yeah, 240 watts. That's pretty beefy. All right, well, these boards are no joke. So let me get that out of the way. And then this looks like a bunch of power cords and a USB cord. Not all that much. All right. These boards usually don't come with a lot of accessories. All right, so that's the power supply, and then we'll take a look at, presumably this is the actual board. All right, there we go. We've got plenty of foam, and that's the board. All right, get this out of here. Sorry if that's a little loud. All right. These bags are not the quietest. Maybe get rid of that with as few crinkles as possible. All right, so there is the Stratix 10 DX FPGA development board. Let me get this box out of the way. All right. So, what do we have here? Well, first thing, we have a tag. That's kind of funny. I guess this is for FCC requirements or something. For use only by product developers, software developers, and system integrators. Well, fair enough. Usually don't see tags attached to stuff like that. That's pretty funny. All All right, let's take a look at what this board has on it. Obviously, we have this gigantic heatsink in the middle, and underneath that, we have the Stratix 10DX FPGA. Let me see if I can get a view of that. That is a huge package. You can barely see that package in there. Let me see if I got something to point with. Let's see here. So that right down there is the side of the package. That's probably one of the biggest FPGA packages that I've seen. That's huge. Let's see, what do we have on this board in terms of peripherals? We've got PCI Express over here. This is a Gen 4 by 16 interface. And then we've got all of these connectors over here. I think these are set up for UPI, and I think it's 2 UPI connectors per link. So there's 3 UPI connections here. And this FPGA, I think, has 4 of the P tiles on it. So one of them is hooked up here, and then one is hooked up to each pair of these guys over here. Then there's 2 DDR memory slots here, and then we have 1 bank of DDR here. And there should be another bank of DDR over here. And then obviously there's the pair of QSFP modules here. And that, I think, just about rounds it out in terms of actual peripherals. These type of boards tend to be kind of Spartan. I mean, you look at this and it's got a whole pile of components on it, but most of these are just related to power. Like all of these capacitors, that's just power. All of this, just power, just power. That's power supply. Oh, that's a configuration flash, I think, and that's another flash chip. It says WinBond on it. Yep, that's a flash manufacturer. This chip over here is kind of supporting circuitry for the QSFPs. Let's see, what does this one do? It sits on the I2C bus from the FPGA, and it basically does level translation, and it has, I guess, LED drivers in it and drivers for the low-speed control pins on these modules. So that's what that does. There's a few little dip switches on here. All of these little switches over here, I think, are in relation to the some of the control lines for the UPI connectors. But that's about it. There's not a whole lot on the board. There is CPU reset. There's another button over here. What is that? User push button. Okay, that's whatever you want it to be. PCIe reset, and I believe that's a Max 10 FPGA reset. So the other thing that these boards have on there is there's a Max 10 board management FPGA. So this provides both the USB JTAG. Well, actually, there's a Max 10 FPGA, there's a Cypress chip here, and then a USB port. So the combination of those gives you the USB JTAG, and then I think this also has a component for loading the bit file, or the Altera equivalent, or the Intel equivalent of a bit file onto the FPGA. And then there's a JTAG connector over here. And yeah, that's about it. Everything else on here pretty much is power. That's power, 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 power. Oh, ICS. That's probably clocking. That's clocking, but yeah, like everything else on here is power. If you look under here, you can see these big metal blocks. So those are going to be cooling for the switching transistors for the core voltage supply. So yeah, like everything else on here pretty much is just power and other supporting circuitries. These don't have all that much in terms of, again, they don't have much in terms of peripherals. The fan connection is there, and then there's a big honking power connector over here. All right, I guess I can turn this on real quick, and we'll see how loud it is. Let me get the brick. All right. And I guess the other thing that we got to figure out too is where the power switch is. There's a power switch right here. All right, let's see here. A little bit. All right, plug this guy in. Okay, turns out it's not too bad. That's interesting. The power switch does not actually control the fan, but it does turn, I guess, the FPGA on and off. That's kind of annoying, actually. It'd be nice if the power switch turned everything off. That's usually what you expect with a power switch. All right, well, I'm going to set this aside for now. We're going to go ahead and pull out the Stratix 10 MX development board and take a look at that. And then we will fire up Quartus and see what we can do after that. All right, here's the other one. the other board that we got. So the Stratix 10DX, that supports PCIe Gen 4. The Stratix 10MX only supports PCIe Gen 3. It has different tiles on there, but this supports HBM. So this one, I believe, has 16 gigabytes of HBM in 2 stacks of 8 gigabytes. All right, let me get that out of the way. All right, close enough. All right, let's take a look at this. If I can get the box open. Okay, there we go. Woohoo. All right, what do we got? A bunch of ROHS stuff, a bunch of warnings. Why do you need so many warnings for a Frappin FPGA board? I don't know. Ooh, this one is packed rather nice. See here. See the way they have this foam cut. That's pretty nice. Okay. Well, here's some power cords. We got, there's 2 of the US style ones. Interesting. Maybe they think we're going to lose them or something. And then a couple international ones. I guess this one is the foot killer. You would not want to step on that with the prongs pointed the wrong way. Oh boy. We have another gigantic power brick. This one looks the same. 12 volts at 20 amps. Let's see, does this have a rating for power? I don't know. It doesn't say. It just says 12 volts at 20 amps. What was the other one? What was the other one? Is that also 20 amps? Yeah, 12 volts at 20 amps, 240 watts. So basically the same thing. And I'm assuming it has the same pinout on there. So I'll leave that in here for now. We'll just use the one for the DX. All right. Wow, look at the metal box on that thing. All right, let me go ahead and get this open. Again, sorry for being a little loud there. Wow. That is quite a metal box on that card. Let me get this, get all this out of the way real quick. All right. Come on. Get that out of the way. All right. Let's take a look at this. All right. Zoom in. Okay. So this one looks very different from the other one. I don't know why they designed it with this like wind tunnel almost. That's quite interesting. Let's see. So on the back we've got 2 fans. We'll have to see. One thing I've noticed with fans is that they tend to be kind of like dogs, right? The annoyance factor is inversely proportional to the size. So this one has me a little worried. This could be a very noisy board. All right, so what do we got on this board? We've got PCI Express. We got 2 interfaces actually. We got a connector on the top here, which can accept some other board, I suppose. And then we've got one here which can plug into a motherboard. So this would be an endpoint, and this would be like a a root port or a switch port. Interesting. I almost wonder how hard it would be to basically turn this into a PCIe protocol analyzer. That would be fun. You could put a card under test in here and then capture all the traffic. That's something I plan on working on soon though. Okay, so what have we got over here? Again, like the other one, there's not very much on this board. Most of these components on here are all related to power. All of these big resistors are all just current sense resistors for power supplies. And then there's other, like there's linear technology components and maybe some level translators. There's also another Max 10 FPGA. I think that's what that is anyway. Presumably, yeah, that looks like a Max 10. That'll be for the board management and JTAG. And that's about it on the bottom. All right, let's take a look at the top. Get this cover off. Zoom out a little bit so we can see the whole card. Let's see. Get all this unscrewed. Okay. All right. Ooh, that's very satisfying the way that latches on there. Wow, this thing is seriously built like a tank. Jeez. Okay, look at this. This is more than 1 millimeter thick on the edge. Wow. I don't know why they did that. I don't know what the point is, but this must be like either water jet cut or laser cut, considering the texture. But yeah, they got 3 little kind of hooks here that connect with the top cover, connect with these pins to hold it on. Neat design. I mean, I would have to look at what the list price on this board, but for the list price, it's you would expect a well-built board, but usually you don't expect something like this. All right, let's see what we got inside. Obviously, we got the fans here. All this is power, power, power. And then we have 1 bank of DRAM. It looks like, what is that, 5 chips? So usually the way they do this is it's a 72-bit interface, and they use 16-bit chips. So 4 of them will give you 64 bits, and then they use 8 bits on the last one to provide the ECC bits, basically. So that's pretty common. That's why you'll see, 5 chips or 9 chips, is because they're making a 72-bit interface. Then there's also a DDR4 module on this side. And I think that's the same kind of thing. 1, 2, 3, 4, 5. Oh, hang on a second. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, so there's 9 chips on here. There's 5 on this side, and then 4 on this side, plus the registered chip in the middle, because this is registered DRAM. Yeah, PC4 2933, nothing particularly special. You can probably get faster and larger memory modules. But one thing that's, hang on, this is 1R by 8, so this only has 1 rank on it, which I think is, I've noticed issues with the Xilinx FPGAs in terms of the number of ranks. If you have a lot of ranks, or if you have more than 1 rank, then the maximum frequency that the FPGA supports drops. I don't know why, but that's how it works. It's got to be for electrical reasons. All right, what have we got on this side? We got a pair of the QSFP modules, and then we've got a Silicon Labs chip here for clocking, and we've got a Cypress chip for the USB. So that chip plus the Max 10 is what's going to give you the USB JTAG. Oh, and then there's a config flash over here, I think. I believe this is a QSPI flash chip for the FPGA. And there may be another flash chip for the Max 10. Not sure about that. JTAG connector here, if you want to plug in a bit blaster or a USB blaster. And then there's a power connector here. The FPGA is obviously underneath the gigantic heatsink here. And then there's also this interesting expansion connector. A very high density connector. I think they call this a high-low connector, and they make little plug-in boards which either have SRAM or DRAM that can plug in here. They didn't give me one of those, but it is what it is. At least I didn't see one in the box. Maybe I missed it. All right, well, let's go ahead and plug this in and see how loud it is. This one does have a power switch on the back as well, so we'll take a look at that. All right. I'm going to put the top cover back on so I don't accidentally overheat something. I don't think that'll be an issue. All right. Let's get the power supply over here. Go ahead and get this guy plugged in. All right, where's the switch? There's the switch. Oh boy. Prepare for takeoff. This one is pretty loud. Yeah, that's annoying. Well, that's about what I expected from looking at those fans. Okay. Next step is to go ahead and get Quartus fired up, and we'll see what we can do with the board here. So the other thing I got is a QSFP cable that's running to a Mellanox NIC in my desktop machine. So I'll go ahead and get this plugged in, as well as a USB cable. And then we can go from there in terms of getting these things operational. All right, one moment. Okay, so let's go ahead and get switched over to using Quartus now. Previously, I've gone ahead and set up the kind of project files. So main thing we're going to be looking at is the tiles on these devices. Now, one of the big differences between Xilinx and Intel FPGAs is that Intel uses their, they call it Emib technology. Somewhere they have, where do they have the drawings? So maybe they're over here. Yeah, here we go. Okay. So Intel has this thing called Emib that means that they can build chips by attaching these tiles. And this is in contrast with the Xilinx devices that I believe they do use multiple die, but they use an interposer that's, you know, the full size of the chip, as opposed to these smaller Emib dies. So the one thing that I always wonder about in terms of this is how you get everything to align correctly, because I know the bump pitch on these things is really, really fine. So getting all of these separate die to align, that's got to be a challenge, but I guess Intel has it figured out. Anyway, there's a number of advantages to using these, probably mostly from Intel's standpoint. But the idea is that you can have a single FPGA die in the middle that has all of the FPGA logic on it, and then you can add separate tiles around the edge connected with this Emib technology. So you can put a varying number of tiles and various combinations of tiles, even with the same FPGA die in the middle. So they have a whole bunch of different parts that have different combinations. So like the GX devices, they just have this L tile / H tile. The TX devices have E tiles, and the MX tiles have the H tile and the HBM2, which I guess they don't use the Emib to connect to HBM2, but anyway. So what we're going to do today is take a look at both the E tile and the H tile. So on the Stratix 10 MX, I have, well, it has 4 of the H tile. Let's see, which is the one that I have? This is the one that I have on there, right? Because it has a 16 gigs of HBM2, so it has 4 of the H tiles. And I have the schematic. Let's see here. Right, here's the schematic. This is kind of a block diagram of what's on the board. There's a Stratix 10 MX FPGA. It has 4 of these transceiver tiles. 2 of them are connected to PCI Express, and the remaining channels on those are connected to under the 2 QSFPs, and then the other 2 tiles are totally unused. So, and what else is on here? Right, we got the DDR and we got the high-low connector, and that's basically it. So, like I said, these boards are pretty Spartan. They don't have much on here. While we have the schematic up, I guess we can take a quick look at what else is going on here. Well, here's the power tree. You're wondering why there's so much stuff on the board? Well, look at all of these different power supply voltages. I think most of these go to the FPGA, but we got, you know, a bunch of stuff supplying the DDR, QSFP, the high-low connector, and some other stuff. But yeah, this is one of the reasons you probably don't want to design your own board if you can avoid it, because not only do you just have to put the FPGA on there, you also have to add all of this additional supporting circuitry. And well, as you can tell, this is pretty complicated. The schematic is 70 sheets. So this has a clock tree, and we can just go over this real quick. Let's see. This is, what is this? The DDR, the slot, right? That's the connections to the FPGA for that. DDR components, 1, 2, 3, 4, 5. Okay, and we can actually see here 16 bits on each one, so these are connected completely. Right, so this is the first 2. There's the second 2, so there's 4 so far, and then the 5th one, only half of those pins are connected. So yeah, that's how you get 72 bits. FPGA end of that, high-low connector. Here's the transceivers. This is one of the unused tiles. This one is hooked up to the PCI Express endpoint, so the edge connector, and one of the QSFPs. And then, yeah, okay, so this is all the endpoint. So that there's 16 channels for the endpoint, and then that. Okay, this is unused, and this one is the other one that has 16 to the root port plus the QSFP. Those are the actual QSFPs, right? We got 4 pairs TX, 4 pairs RX, plus the low speed control. PCIe connectors. Then we get down here to the power pins. I don't know how many pins this chip has, but yeah, let's see. How many schematic sheets do we have just for power? Here is power pins number 1, power pins number 2, power pins number 3. 3 schematic sheets just for power. That's a lot. And then we have 1, 2, 3 schematic sheets just for ground. I always find this hilarious. 3 schematic sheets just for all the ground pins. Yeah, I'm thinking somebody should make a T-shirt or something with the with this on there. Maybe you could say like I'm well grounded or something. I don't know. Maybe that doesn't work very well. It's kind of hard to read this. Maybe it work better as a meme. I don't know. I'm not that creative. Well, who am I kidding? These are ground pins. By definition, they have no potential. Anyway, here is the clock infrastructure, right? So I think the Silicon Labs part, SI5341, this may be the same device as what was on that gigantic high-tech global FPGA board. So we got some more Silicon Labs parts. This is for part of the I2C infrastructure. These, I believe, are level translators. Got some LEDs and push buttons. And this is the Max 10 stuff. Yeah. Oh, and this shows the power again. Let's see. This is the core supply voltage, 132 amps at 0.85 volts. Yeah, that's a lot of juice. That is a lot of juice. That explains why you need so many phases for that. But yeah, then you got all the power regulators and whatnot. You know, these are the core voltage regulators. 2 phases, the other 2 phases. Yeah. So there's a lot that goes into these boards aside from just the FPGA itself. And then if you like capacitors, we have 3 pages of just decoupling capacitors. Yeah. So yeah, there's a lot on there, but there's not a lot in terms of peripherals. So when I say, you know, the board is kind of Spartan because it doesn't have many peripherals, that's what I mean, right? Got a lot of parts, but not much that you can use from the FPGA. It's mainly just supporting components. All right. Let's see. So what I need to do today is bring up one of the channels on the H tile at 10 gigabits per second. So, all right. So I've gone ahead and created kind of a lot of the structure for this already. So this is the top level Verilog file here. Brings in 100 megahertz clock and the reset line from one of those push buttons. And then it brings in one of the QSFP channels. Right, and then that's connected to the core logic, which has the Ethernet MAC and whatnot. Right, so what we're gonna have to do in here is bring the serializers out to XGMI interface, which can be connected to the Ethernet MAC. All right, so let's go ahead and get underway here. So the first thing I'm gonna do, I'm going to go ahead and generate the project file so we can generate the IP cores for the H tile in Quartus. All right. Oh, I need to do. Source the settings file and then make UPF. There we go. All right. Let's get out of the way. Okay. So I'll go ahead and open that up. All right. That out of the way. All right. So here is the Quartus Prime software, Quartus Prime Pro. So using this, what we need to do is create all of the necessary IP components for bringing up the PHY. So this talks a little bit about it somewhere. Here we go, in terms of all the pieces that we need. So what we're going to do is use the native PHY IP core, and we need to generate a couple different pieces, right? We need the transceiver PHY reset controller, which is responsible for monitoring the PLL lock status and resetting everything. Well, not so much resetting everything, but releasing all the resets in the correct order. Then we need the native PHY IP core itself. That's the actual serializer. And then we need a PLL IP core for generating the line rate clock, basically. Actually, in this case, it's half of the line rate. So we're going to be running it, 10 gigabits per second. We run these numbers just so we're all on the same page here.
So it's 10 gigabits per second, but it's encoded with 6466 encoding. Actually, hang on a second. Okay, so 10 gigabits per second. There's your line code. So it's 10.3125 gigabits per second. And PLL is going to have to produce half of that to drive the serializer. So those are the numbers we're going to need. Take a look here. Okay, so I'm going to go under interface protocols. Hang on a second. Yes, here we go. Transceiver PHY and transceiver PLL. So these are the components that we're going to need to generate. And in fact, I think there's one other. Well, I'll deal with that in a minute. Okay, so the first thing we need is the Stratix 10 reset controller and the transceiver native PHY here. Okay, so let's start out with the PHY. Well, let's go ahead and fire everything up. There's 3 different PLLs. For the high line rate stuff, you just need the ATX PLL. The other ones are a little more limited. Okay, so this one, call this the PHY. Oh, I'll call it the transceiver. Okay, and then this one is going to be the okay, and then I also need the reset controller. All right, so one thing I'm going to do that's a little bit non-standard is that I'm going to set up the transceiver for operation at 25 gigabits per second first, and then I'm going to drop the line rate to 10 gigabits per second, because eventually I need to be able to run it both. So this is the reset controller. Okay. Fortis is being a little slow today, apparently. Okay, so here is the PLL IP. Give that a minute to get itself figured out. All right, there's the reset controller. The reset controller is the simplest one, so that starts up pretty quick. This one takes a little bit longer, and it still has not opened up this one yet. Yeah, all right. While that's thinking about things, let's take a look very briefly at the block diagram for these tiles. Let's see here. PLLs and block networks, that's not what okay, yeah, the PHY architecture. What do we have here? Okay. All right, this is what I was looking for. So this one shows the actual data path that's running inside of each one of these tiles. Can I zoom in any more than that? No, you're not going to let me? That's annoying. Go figure. This is a GNOME application. Doesn't let me do stuff that I should be able to do. Okay. So there's one of the major differences between the Intel components and the Xilinx components in terms of the serializers is that the Intel ones actually have a lot of additional hard logic for supporting various protocols. So let's see. On the transmit path, well, the other thing too is they need additional hard logic to support the Emib interface. So what's actually not shown here is that there's an AIB block on both sides of the Emib that you don't actually see because it's, you know, buried inside of the IP core, but it is there. So yeah, in the transmit direction, you go through a FIFO, and then you go through AIB, and then EMIB, and then AIB, and then another FIFO. And then you can go through various blocks to support various protocols. So this supports interlaken. 6466 is for, you know, 10 gigabit Ethernet. And then the scrambler is also used for 10 gigabit Ethernet. And then interlaken disparity generator, I guess, is for interlaken. And then this goes through the gearbox and then out onto the wire. And then they also have some components for forward error correction. There's, what is this, transcode encoder, KR-FEC encoder, KR-FEC scrambler, and KR-FEC TX gearbox. So all this stuff is required for adding the FEC. And then that goes through the serializer and out onto the wire. So for Ethernet, generally what you want to do is to turn on the 6466 encoding and the scrambling. But unfortunately, I think there are, basically line rate limitations in terms of what speed those things will run at. All right, so let's go ahead and see if I can pull up a basic 10G base R configuration here. So they actually have a library here, so I can select 10G base R and hit apply. So this will load up kind of a standard set of settings for 10G. But like I said, I want the configuration to also work at 25G. So, well, one thing I need to do is change this to 1.1 because that's the actual voltage. And then it's LR. That's that. Okay. LR. All right, there we go. Let's see. All right, so for 25G, the rate that I need to run at is going to be a little bit higher. So I'm going to multiply this by 2.5, 25.78125. That's the number that I need. So this is 25.7825. Okay, there we go. Now let's see. Give that a second to update, and this gives me a bunch of errors. So we need to select a GXT channel. That's expected. Okay. And let's see. And this, okay, I need to check enable background calibration. Yep, okay. Okay, and then it's also not happy about the data rate parameter, probably because of some other settings. So what we need to do now is go into ECS, make some adjustments. So I think I need to make that 64, probably. I don't know if that makes a difference. That didn't change much. Okay, let's just start turning stuff off until this works. Okay, so I'm going to turn off okay, so with this set to 66, that will turn on the gearbox. Let me try turning off the encoder and the scrambler, and we'll see if that helps. Okay, so that is now giving a different set of errors. Still not happy about something. I think it has something to do with the FIFO settings. All right, come on. This is being very slow for some reason. All right, well, whatever. So the main thing that I need in the transceiver for what I'm doing is the gearbox. So there's a TX gearbox and there's an RX gearbox. And the reason you need the gearbox is because the serializer is always basically a power of 2 width, possibly with some factors of 5 because of all the AP10B stuff. So this can be like 16, 32, 64 bits. But for 10G Ethernet, we're moving 66-bit frames. So the gearbox is responsible for, making that conversion. The idea is that on one cycle, it will accept 66 bits, and then on subsequent cycles, it will output, 64 bits. And you'll have to have a gap on the input or the output, depending. Wow. This thing just decided to completely hang on me. Doesn't seem to be completely hung. All right, let me restart this. Neither the Quartus software nor the Vivado software is particularly great. They both have some issues here and there. Come on. Oh, that's not working. Let me kill this. Start it up again and see if it will work this time. All right, back to Quartus. I need PHY IP. Try this again. Okay, so this is a transceiver. All right, try this again here. Wasn't expecting Quartus to put up quite this much of a fight. Once this is done, then we can generate the verilog for this and start integrating all the pieces. While this is thinking about stuff, I'm going to go ahead and put in some of the kind of boilerplate code that's necessary for this to work. So for the Stratix MX, first thing we need to do is add some clock and reset code here. So this is an IP I'm going to have to generate in a minute. This block called reset release. And this, I'm actually not quite sure what it does. I need to look at the documentation a little bit more carefully, but it's you're supposed to put it in on these larger devices. Let's see here. Okay, so oops, and init. So we start with that, and then I'm going to take 100 megahertz clock, right? I'm going to pull that in from the system clock pin, just so I have a slightly nicer name to work with. And then I also have a reset line, and then I need to use my little sync reset module. So what the sync reset module does is it synchronizes an asynchronous reset input with an internal clock. So I have this guy set up for the 100 megahertz clock, and N4 means it's going to hold the reset for 4 clock cycles. So I connect the clock 100 megahertz. Okay, now where am I resetting this? All right, so this is an active low reset, so it's not CPU reset in, okay, or in init done, okay. So the init done signal will go low once the init is complete. So if it's high, then we're going to hold it and reset. All right, let me out. That's going to be reset 100 megahertz. Okay, cool. That's simple enough. All right, and now for the PHY interface. Actually, take a look at the orders. Ready to go. All right, let me try this again here. Okay, 1.1 volts. Gotta wait a second. On LR. All right. Okay, so this is going to be 2578 1.5. Okay. To be GXT. Okay. Oh, I forgot to load. The 10G preset. Hang on, let me do that first real quick, and then again 1.1 volts and LR, and that's going to be a GXT and 25.78. Okay, there we go. All right. Oh, actually, I think what I need to do is change this to basic enhanced PCS. I think that might have been one of the things that was tripping me up before. Okay. All right, there we go. That's better. I think that's right. All right, so not bonded. We're just making one channel, so there's no channel bonding. Preset reset sequence. Leave that independent. We don't want to divide the clock. Okay, that seems fine. We need to enable background calibration. All right, RxPMA. Okay, so one reference clock. The frequency is going to be 644 megahertz. I think it gives you a bunch of options, but that's the one on the board. This seems to be the standard one that Intel uses. Does this support? One does not support 156, but I think it supports 161. Yeah, that also supports the standard 161. Okay. All right, so that looks fine. All right, so now we go here. I'm going to change to 64, and then I think a bunch of these need to be turned off. Okay, so the encoder and the decoder are not going to work at this speed. I'm also going to turn off the scrambler. I'll do that in soft logic. Okay. Okay, let's see. Turn off that. Also turn off the block synchronizer. I will do that manually in the PHY IP core, or in the PHY core that I have. All right, now this seems to be stuck again. Really? Really, I just did this a couple days ago and it was fine. All right, well, while I let that figure itself out, I'm going to continue putting in some of this interface code here. So next thing I need is all of the connections for I need to define all of the XGMI connections. So let's see, and also the low speed control signals for the modules. So there are a couple different signals for the modules. Take all of these for now. Get rid of the inputs. I need to drive all the outputs to specific levels. So let's see here. So I want to make sure the module is selected. I'm going to take it out of reset and out of low power mode. Perfect. L in this case means inverted. I guess L for active low probably. Okay, and then I need to go ahead and put in all the internal connections that I'm going to use in a bit. All right. So I have a TX clock 1 int. Okay. TX clock 1 int. Okay, and then I TX reset. Okay. I have TXD, and then this one 63 to 0. I have XC. So the XGMI interface consists of two signals. Plus the clock and reset and whatnot. The D contains the data, and the C contains basically control flags. So the TXD will carry either control characters or data characters that are all 8 bits wide, and the TXC, it's 1 bit per 8 bits in TXD that indicates whether that byte is a control character or a data byte. Okay, so that's TX for channel 1, and I will do all this for RX. Okay. Okay, and it's going to be for 2 and channel 3 and channel 4. All right, so that's all for the first QSFP, and then I do all this again for the second one. Let's see here. Okay, cool. Now let's see if I can generate this IP core. What the heck? What is going on with software today? Dang it. All right, I'm just going to generate these from memory here. This one, so I can get them all closed and out of the way. So this one we have 1 transceiver channel, 1 PLL. We're going to run the clock frequency at 100 megahertz. That's just the free running clock for the time values. Use fast reset, that's fine. We're not going to simulate it. Separate ports per channel. Well, there's only 1 channel, so it doesn't matter. Enable TX channel reset control, separate per channel. Sure. These are fine. PLL cal busy, need that. Digital reset mode, that's fine. Okay, so I'm going to go ahead and generate that. So this one has inputs from the PLL and the channel modules indicating when things are locked and ready to run. So this will hold everything and reset until the PLL is locked and whatnot, and then release the resets in the correct sequence with the correct timing. Not particularly complicated, but kind of important to make sure things work correctly or start up correctly. Okay, so I'm going to go ahead and close this. All right. Now this is the ATX PLL. This is used for generating the line rate for this guy. So let's see. Protocol, that's fine. Bandwidth, I can set it to low bandwidth. The lower the bandwidth, the longer it takes to lock, but the less jitter you have. Okay, so this is 1.1 volts. We have 1 reference clock, select 0. GX clock output buffer, because we're going to run at 10G. Okay, so I can ignore all the GXT stuff. And then the output frequency, calculated that, right? It's 5156.25. Okay, so we let that think about it for a second, and then the reference clock is going to be the 644, right? Okay, that looks good. I think all of these other ones are going to be fine. All right, excellent. That looks good. I'm going to go ahead and hit generate HDL here. That looks good. Okay, generate. This one seems to have gotten hung up again. Dang it. All right. Well, got to restart it again. I got to restart it again. I don't think Vivado has given me this much trouble. They new. All right, let me kill that. Let's try that again. I'm actually going to totally quit out of Quartus for now. Make sure that things get sorted out correctly. Okay, both of these are here. All right, close that. Restart Quartus. See if I can generate it this time. Okay. Fortunately, my computer is pretty fast, so Quartus starts up pretty quick. Okay. The memory interface is a protocol. No. Interface protocols, transceiver phi, L tile, H tile. Okay. All right, let's go ahead and create that. All right, so while that's running, I'm going to go ahead and start plopping down some of these modules. So when it generates the IP, it generates some associated Verilog files. So this one has the instantiation template for the reset module, for example. So I'm going to go ahead and put this in. Okay. Still working. Okay, so for this one, this needs a just a free running clock. So I'm going to use a 100 megahertz clock and 100 megahertz reset for that. Okay. All right. Let's see. And then most of these need to be connected to either the transceivers or the PLLs or some combination. So what I'm going to do is actually select all of these, right? And then I'm going to create wires for all of these connections. Okay, so I'm going to call this 0, FP0, receiver. Oh, well, I guess, yeah, I'll just do that. Okay, these are all wires. These are all, I think these are all 1 bit. It says over here, they're all 1 bit. Okay, perfect. All right, so now what I can do, wonders of using the wonders of Sublime Text here, I can go ahead and replace all of these. Didn't work, hang on. Let me copy that. Okay, paste, there we go, that's better. And then I can call these all QSFP0. Okay. I got that. I go all of that. Okay, perfect. All right, so there is, actually I need to rename this. Okay. Need to rename this. Okay. FPGA reset instance. Okay. There we go. So that is the reset controller. This done. All right. This is running again. All right. Let me just go through from memory what all of the settings need to be for this to work. This GX, that's fine. Enhanced PCS. Okay, there we go. Basic TXRX duplex, 1 channel. This is 10.3.1.5. Okay, that's fine. Let's see. So this is going to be at 644, right? That looks good. This PCS sets it to 64 and this to 66. All right, so that will turn on, like I was talking about before, it'll turn on the gearbox so that we have a nice 66-bit output. And let's see, what else do I need here? Do we need anything else here? I don't think so. All right, let me go ahead and take a look at the FIFOs. Need to adjust this here. This is saying I need 10. And I think the same thing here. Okay. Is there anything else that I need to turn on? Yes, clock out. Oh, all right. So the clock output on here. So one thing that I need to do is actually take advantage of these FIFOs. So there's a couple different clocking paths that are set up inside of these transceivers. We'll just take the RX path, for example. The data comes in here, the CDR recovers the clock, the deserializer then deserializes it. So you get 1 bit wide coming in here at line rate. You get, 64 bits coming out here at line rate over 64. Makes sense, right? This is a high-speed clock. This is the divided serial clock. Okay. So this is going, so in this case, this would be like 161 megahertz at 64 bits. And then you go through the RX gearbox, but it comes out here, it's still at 161 megahertz, but not every cycle actually contains valid data, right? So this comes all the way down into this, this RX core FIFO. So it goes into this FIFO in the internal clock at 161. But what we're going to do is take the RX PMA div clock out, which is a divided version of the high-speed clock. And instead of dividing it by 64, we're going to divide it by 66. So this will be running at 156 megahertz. And if this is all set up correctly, then we basically remove these invalid cycles. So every cycle coming out of this FIFO will actually contain valid data. So that, let's see. Turn this on and we divide by 66. All right, very cool. Divide by 66, TX, clock in. Okay, I think that's correct. Analog PMA settings. We just turn this on, all tap adaptive DFE. Okay, seems okay to me. That off, I don't think I need to do that. PLL type, all right. I think we might be okay here. You just double check. Don't need any of the FIFO ports. Don't need to touch that. I think that's fine. Oh, actually I need to, I think there was one other thing that I need to do. Yes. Go ahead and make sure these are set to enable. I got tripped up by that before. It was very perplexing. Okay. And then I think I left all this stuff off, right? The main thing I need is to make sure that this is 66. All of the frame generators are turned off. Not using the error checker, not using the encoder. Implement that myself. Scrambler, descrambler off. Block sync, I'm going to do that myself. Okay, cool. I think we're good. I'm seeing everything down here all green, so this is ready to generate. All right, go ahead and generate that. And okay, cool. That's going. All right. That will take a moment. Once that's generated, then we'll have the template that we can go ahead and paste in. In the meantime, I'm going to go ahead and get the PHY module set up here. Oh, I also need the PLL, right? I need the PLL and I need the PHY. Okay, so PLL, I'll go ahead and do that next. There's a reset controller. Here's the PLL. PLL instantiation. Oh, this is much simpler, right? So go ahead and put that in. The PLL inst. Okay, so ref clock. This is going to be QSFP. All right, what was that signal called? Okay. Oh, ref clock QSFP0. All right. Okay, there's that, and then I need a TX serial clock, PLL locked and PLL cal busy. Oh, so these two are already defined, I think. QSFP0, PLL locked, right? And QSFP0, PLL cal busy. Oh, there's actually one of these I need to change. There's PLL select. I don't need that. This one is going to be that's just going to be tied to 0. Okay, cool. And then I need to make one more signal. I need serial clock. Wire USFP0 EX serial clock. Well, clock. Okay, cool. So that is the transmit clock that's going to be connected to the actual transceiver channels. Okay, there we go. So we have the reset, we have the PLL. Need to generate one more thing. There's the reset release IP thing that I need to do. There it is. This one is done, so get rid of that. Okay, so reset release. Okay, there we go. I don't think I need to do anything here, just generate it. Okay, perfect. So I'll go ahead and generate that. Yep. All right. I think I have all the IP cores that are necessary now. It's a question of whether I have all the settings correct. I think I do. Oops. Let's let that run. Okay. That'll take a moment. All right. So the next thing I need to do is put in the actual transceiver instance. So I go, here's the transceiver instance. Here we go. Okay. All right. So the transceiver here, we got a bunch of reset lines: analog reset, digital reset, analog digital reset status. So all of those are just connected to the reset controller. TX and RX cal busy. Again, those are just connected to the reset controller. Serial clock, that's a serial clock here. DDR ref clock, that's the original ref clock input here. Okay, let's go with that. It's going to be USFP0 TX serial clock. Okay. And then we have the TX and RX serial data. So this is the QSFP0 TX TXP0. And again here, QSFP0 RX0. Okay. So that's that. And then more of this stuff is just going to the reset controller, it looks like. Okay. Oh, I need to check a different box. Dang it. Moment. That's fine. I missed a box. All right, let's go over here. So the thing is, the transceiver interface through AIB is fixed at 80 bits. And as you reconfigure the transceiver into different modes, different parts of that 80-bit signal are used for different things. And if you check a particular box here, it will generate the necessary kind of reshuffling logic to put it on a couple of particular ports that you can just use. But I forgot to check that. So, all right, we'll deal with that in a second. Let me get all the reset related stuff connected. All right, let's see here. Those are all okay. Start with that. E0. Okay, so I think that's all of that. Okay, and then lock to ref. This needs to see lock to data, but not lock to ref. That's fine. Okay, there's lock to data. Okay. We have the core clock in, core clock out, and parallel data. Okay, so create a couple of more connections here. So I'm going to need. Oh, some of these I guess are already defined, aren't they? Right? I've got already have some of the clock and reset lines defined up here. So what I'm going to do is I'm going to TX and RX clocks that I already have defined. And so the TX clock out, connect to that. Okay. And same thing for the RX clock. All right, RX clock out. Loop the RX clock back in. All right. And then the TX and RX parallel data, I need to sort those out in just a moment here. I want the simplified data interface. Yes, check that. All right, now regenerate. Oh, and I will also mention that this does tell you what the PLL configuration needs to be. The external PLL must be set up for 5156.25 megahertz. So we didn't necessarily need to compute it, but you know, because this thing was being annoying, that made things a little bit more expedient. All right, let me see if this was updated. Nope, that'll be updated in a minute. Okay. So now what we need to define are the signals that connect between the transceiver and the PHY instance. So this is going to be 64 bits of data plus a 2-bit header. Okay, so this is going to be the TX header. Okay, and this is going to be 2 bits. And then 4 bits data. All right, so there's the TX, and then we have the RX. Okay, this update, that did update. Excellent. Go ahead and see. Yeah, all right, so that just replaces these last 2 lines here, like so. Okay. All right, so TX parallel data is the QSFP0 XCVR TX data. As you can see, this is 64 bits, so that's correct. Rid of all of these. Okay, and then we have the TX control. So this is QSFP0 TX header, right? Okay. And then we have the data valid, and that's just going to be tied to 1. Okay, and then there's the additional data lines, which it gives you the balance of those. This is the balance of those 80 bits, and we're not using those, so we just tie it to 0. And then we have the RX parallel data as well. So QSFP, RX, QSFP, RX data. Okay, and then again, QSFP, RX, QSFP 0, RX. Oh, it's the header. Okay, there we go. Excellent. All right, cool. And then we're going to ignore data valid and the unused output. Okay, cool. And currently the PHY implementation that I have doesn't support, not every cycle being valid. So not that big of a deal. All right, let's see. So now the next thing I need to do is pass a couple of clocks around, generate a couple of resets, and then instantiate the PHY core. We'll see what that looks like. All right, so the first thing I'm going to do is I'm going to grab my reset controller that I have up here, and I'm going to paste that down here, and I need to use this for both the TX and the RX. So this is QSFP0 RX. All right, what did I have up here? This is RX FP0 RX reset 1 core. Okay. Well, I guess I got the TX now, so I'll start with the TX. Okay, so the clock is going to be the TX clock, right? So this is a TX clock. All right, and then I'm going to reset when one of the outputs from this reset controller is indicating that it's not ready. So this is a TX, so I need to look at the QSFP0 TX ready signal. Okay, and I'm resetting it, but it's not ready. Okay, and then this provides the RX reset. Okay. Oh, and then these are going to be int and int. Okay, so there is TX reset, and then I copy that, and then this RX, all these TXs. Oops. All right, so all RX, and this one, that one should have been TX. Okay, cool. And then one other thing I need to do is the core needs to run at 156 megahertz. So I'm just going to steal the first transmit clock and use that. Right. That's just going to be equal to transmit clock and reset. Okay, very cool. All right. Nice. Now the last thing that I need here is the actual PHY IP core that does all of the conversion and whatnot. All right, let me take a look here. So this one, let's see, this is the PHY ETHPHY 10G. Okay, so this one has a whole bunch of stuff. Most of this is not going to be used. So go ahead and take a look at, copy that. All right. So I can go ahead and convert all of this. See here. Okay. All right, so that's that, and then this is USFP row by 1 instance. All right, here we go. Oh, and I need to put a dot on all of them. All right. Let me make sure I'm using all the right values. So data width 64, width, yeah, okay. Header width 2, bit reverse. It's usually bit reversed. We'll see about that. Scrambler disabled, that's fine. PRBS, we're not turning that on. No pipeline registers for now. Oh, hang on. I have a slightly old version of the code here. All right, that's kind of important actually. Okay, there we go. That's better. All right. The reason I had to change these is because the bit slip timing is a little bit different on the Intel devices. Let's actually just take a brief look at that. This is kind of an important characteristic, is because the way 10G Ethernet works, it moves around these 66-bit blocks. But on the deserializer, you basically need to find the 66-bit blocks, because it's going to lock onto the data just somewhere, and it's not necessarily going to be aligned with these blocks. So what you have to do is what's called bit slipping, where you slip the gearbox by 1 bit position until block lines up. And there should be, I'm trying to remember where this is in here. There is a description of the timing that's required for that. I can't remember where that is at the moment, so not particularly important, but from what I remember, you need a 200 microsecond pulse, so you have to put it high for 200 microseconds, and we're using a 156 megahertz clock, so that's 6.4 nanoseconds, so 200 nanos over 6.4 is about 32, so I'll do 32 clock cycles, and then you got to repeat it maximum every 400 nanoseconds, so another 32 cycles low where you can run it again. Okay, that seems fine. All right, I think all of those are correct. Let's go ahead and connect up all of the other signals. All right, all of these wires. All right. Okay. All right, so the clock and reset, these are going to come from the TX and RX clocks that were connected before, right? So here are the TX and RX, or the TX clock and TX reset. So I'll go ahead both and then rename it. I need to adjust my gate. Okay, RX. All right, so there's RX clock, RX reset. Okay, and then I need the XGMI, or sorry, this is, yeah, so the XGMI interface is going to be these guys here. So go ahead and take, there's your TX side, XGMI, okay, and then I also need the RX side. All right, so TX and RX, and then the series interface. So these are the connections, right? We have data and header, and we also have bit slip. I forgot to check a box again. Okay, fair enough. Let me go over to, I think this was under enhanced PCS. Yeah, okay. RX data bit slip and RX bit slip. There we go. All right. Okay. One more shot here. I think I have all the settings correct. Bit slip port is enabled, and that will regenerate. I'll have to add that in a second. Okay. Let's go ahead and plug all of these guys in. I'll start with the TX data and TX header. All right. Oops, I didn't copy that. Okay, there we go. We got the header and the data, so I'll go ahead and plug these in here. Okay, header and data on the TX, and header and data on RX. Okay, and then I need the bit slips. This I'm going to call QSFP0 transceiver RX bit slip. Okay, I got that. Let me go ahead and define this here as well. Okay, this one is going to go into the bit slip signal, which, okay, that's done. Ah, man, it's not done. All right, RX bit slip, that's going to go right here. Okay, here is the bit slip connection. All right, let me run this again here. Didn't want to do that. All right, there we go. Okay, what else do I need to do? Right, a couple more connections. Status, I can ignore all of those, and the PRBS, I will set these to 0, even though those components are disabled anyway. All right. All right, so this is looking just about right in terms of all of the connections. So the next step is, as soon as this is done, it'll take a minute, I'm going to go ahead and kick off Quartus to actually go ahead and generate this for the Stratix MX. Now that's going to take a little while, so while Quartus is running, I'm going to start working on the Stratix 10 DX board with the E-tile, because that tile has a completely different design. So one of the advantages of the tile-based thing is you can actually put different combinations of hard logic in the tiles. All right, so that looks good. Actually, not quite yet. What I'm going to do in Quartus is I'm going to go ahead and run the synthesis step, and then I'm going to add some logic analyzer probes. So with the probes, we'll be able to go take a look at what's going on the FPGA, just in case, you know, something doesn't work. The one thing to keep in mind is that when you're interfacing with serializers and whatnot, it's pretty easy to make a mistake or have a bad assumption. The documentation is not necessarily perfect in terms of all the descriptions that are in there. So the XP0 does not have a driver. That does not seem right to me here. What happened? I did connect that correctly, right? I think so. X serial data. Okay. Now, QSFP0 LP mode does not have a driver. QSFP0 LP mode should be assigned. I think I forgot to save the file. All right, let me try this again. All right, at least that didn't take too long. All right, let's try this again. Let's run this again, see if this works. All right. So the logic analyzer tool requires that the design be synthesized before it can go through and locate signals. There's actually one pretty significant difference between, between the Quartus tools and the Vivado tools in terms of how the logic analyzer works, or how it's integrated with the rest of the tools. Extra comma in association list is not allowed. Okay, 251. 251 is, yep. Okay. Oh, yeah, I'm just gonna make this 8. All right. All right, cool. Let's try that again. So yeah, with Vivado, I think there's maybe a couple different ways you could use the ILAs in Vivado, but the way I usually use the ILAs is to generate a core for the ILA and then manually, instantiate it in the design and make the connections, which works, but it's kind of a pain. What? Oh, that goes away. All right, third time's the charm, right? Let's let this run here, and I'm going to go ahead and get the logic analyzer stuff running. So in Quartus, it's, in my opinion, significantly better integrated into the rest of the tools. So I can just push the button for the signal tap logic analyzer, and I can create a new one. Yeah, okay, that's all right. There's invalid JTAG configuration. Well, that's fine. I don't have anything programmed yet. Okay, so in signal tap, this is what the interface looks like. So what I'm going to do is create 2 instances. And the reason I need 2 instances is because you need 1 instance per clock domain, basically. I'm going to go ahead and rename these. I'm going to call one RX, call the other one TX, RX and TX. Okay, there we go. Let's see here. Yeah, so this will take a couple minutes to finish up. Once it's finished, then we'll actually be able to search through all of the signals to make all the connections. Right, so I have to go through each one of these. I need to assign a clock and configure it. So I think, let's see, for RX, I'm going to go ahead and make this 16K. Why not about 4 segments? Same kind of thing here, 16K and 4 segments. I don't know if you've ever used integrated logic analyzers before, but they have some kind of cool features. The downside about the integrated logic analyzers is that the sample depth you can use is very limited. Right, generally just a few thousand points. I mean, what's the biggest number they have here is 128,000 points. If you use an external logic analyzer, you can have much deeper sample depths. The reason for that is because these use just the internal FPGA RAM to store the sample data. But the advantage is these run synchronous to the internal logic, which is really useful. Because you might be running at a few hundred megahertz. If you want to hook up an external logic analyzer at a few hundred megahertz, I mean, 1, you need a lot of pins, and 2, that's a pretty major signal integrity challenge to make that sufficiently reliable. So yeah, being able to make all this stuff work internally without having to consume a bunch of IO pins and deal with all sorts of annoying signal integrity, and being able to run really wide interfaces is very useful. But the flip side, you kind of have to use these with care because you can't probe everything and you have a very limited sample depth. But they can offer some pretty excellent capabilities in terms of visibility into various parts of the design. So I have 2 of these set up now. I gotta wait for synthesis to finish before I can finish that up. All right. So we're going to set this aside for now, and meantime, I'm going to take a look at the eTile documentation real quick, and we can get cracking on the Stratix 10 DX. So let's see. Okay, so the eTile is quite different from the H-tile. The eTile actually supports the MAC layer as well, right? The H-tile, let's see, what does this talk about here in terms of the overview, in terms of protocols and whatnot? Well, I was looking for a nice protocol list. I don't think it has that. These basically only have the phi level components, right? Oh, this has a comparison a little bit between the different tiles, right? So this one supports up to 28 gigabits per second. The eTile actually has PAM4 capable SerDes that run much faster. This is 57.8 gigabits per second. So that's what you need for the 2-lane 100 gig stuff, or 1-lane 50 gig. But the eTile, the advantage of that is it also has a lot more hard logic, right? So this has all of the RSFEC components and all of the, it also has hard max, versus the H-tile. Actually, the H-tile does have some hard logic. Okay, here we go. That's the figure I was looking for. Okay, so this is what the H-tile looks like. It has FIFOs for interfacing with the FPGA logic on this side, and then it has all the serializers and the PLLs for the external interface over here. So if you don't use any of the the hard IP logic here for 100 gig Ethernet or for PCI Express, you basically have a one-to-one mapping all the way across here. So you have the FIFO on both sides, plus the PCS and the PMA, going out the door for each one of the channels. So there's 24 channels here, I think. Yeah, 6 times 4 is 24. So you get 24 of these guys. But it also has PCI Express hard IP. So if you want to turn on PCI Express, you can use 16 lanes with the hard IP here. And then it has a 100 gigabit per second Ethernet MAC. So you can use this along with channels 0, 1, 3, and 4 to bring up a 100 gigabit per second connection. But this only works for 100 gigabit, and I need to check to see if it supports RSFEC. I think it does. But the E-Tile has a little bit more stuff in it. It's a significantly more advanced core. So let me see if there's a block diagram around here somewhere about what's going on. Okay, here we go. This is what's in the E-Tile. There are 12 PMA channels. Actually, I think it also has 24. I think there's basically 2 of these groups inside of the E-Tile. So each one has 12 channels, and then on the other side there are 12 connections through EMIB to the FPGA core. And then there's a bunch of different hard logic here. So there is a pair of 100 gig Macs. So these Macs can use the top 4 and the bottom 4 lanes. And then there are some additional Macs here for either 10 gig or 25 gig. So this gives you a bit more flexibility, and it reduces the amount of logic you need on the FPGA, because you could use the 10 gig or 25 gig Macs if you're running at 10 or 25 gig, or you can switch to using the 100 gig Mac. And having all this in hard logic, saves logic resources on the FPGA. And then these also have hard FEC as well. So you can either use one FEC block for 100 gig, or I think you can split it for 10 gig or 25 gig. I guess this is RSFEC and the 10G base KR FEC, which is a little bit different. So the FEC is the forward error correction, and that's what you use to get a decent error rate at higher bit rates. All right, let me see if Fortis is done. It is done. Okay, cool. So let me go ahead and add all the signals that I need. All right, so in the RX direction, let's go ahead and set this up here. So I'm going to go ahead. I need to look for, okay, I'm going to look in, let's see, the PHY IP core, the first one. Yes, that's right. Okay. Okay, hit search. Takes a moment. Okay, so this is for the clock. So I'm going to take the RX clock, right? There we go. Hit select RX, right? Yeah, okay. There's the RX clock. Okay, now I'm going to add a bunch of signals. Same kind of thing. Okay, put the star there. Then we're looking in the PHY module as well. Okay, great. I'm going to go search. All right, so what we're going to do is we're going to look at, well, first some standard control signals, right? So I'm going to look at the RX reset, RX high BER, RX block lock, and should be a bit slip signal. Yeah, SerDes RX bit slip. Okay, so we got all that. And then I'm going to look at the SerDes connection, right? So I have the SerDes RX data, SerDes RX header. Let's see. Let me go into here. I'm going to look at the encoded RX data and the encoded RX header. And then finally the XGMII RX data and RX control. Okay. So this kind of gives you a view through several different components of the PHY. All right, so that's that. That's on the TX side, or that's on the RX side. Now let's set up the TX side. So I'm gonna do the same kind of thing. Yeah, that looks good. Go ahead and search. On this side, I'm gonna look up the TX clock. There's a TX clock. Okay, got that. Let's add all these nodes. All right, so we have TX reset, right? TX reset, and then I'm going to go the other way on this one. I'm going to start with the TX or XGMII TX data and TX control. And then I'm going to go over here and I'm going to go ahead and put in the encoded TX data. All right. And then finally the SerDes TX data and TX header. All right, and then I'm going to do one other thing. I'm going to go into the FPGA core. And you notice, or you remember from before, I went ahead and took the transmit clock domain, or the transmit clock, and connected that to the the core logic. What I'm going to do is pull up several signals from the core logic. All right, core. So I'm going to go ahead. I'm going to see the transmit and receive data here. So I have, let's see, start with RX. Okay, so there's half of the RX, and then I got to go down here, RX data and T keep, and then TX everything. Okay, cool. And then I got to go down TX T data and T keep. Excellent. All right, so we'll go ahead and put all those in. All right, excellent. That looks good. So I'm going to go ahead and run that. All right, great. So that's saved. All right, so now this is going to go ahead and run the whole smash, and when that's done, we'll put it on the board, and we'll actually be able to get a view of what the PHY is doing inside the FPGA. All right, and if it doesn't work, then we can get some idea of what's going on and how to fix it. So that's the first step. This is now running, so I'm going to go ahead and set this aside. Well, I'll just leave it in the background, and we will revisit that in a few minutes. All right, so now let's take a look at bringing up kind of the same thing, but we're not looking at the PHY, we're only looking at the E-tile. So this is much simpler because it's basically just the Ethernet MAC. So there's a lot less logic that's required. All right, so I'm going to go ahead, same thing as before. I'm going to go ahead and open up the project here. All right, of course, the Terra Tortoise Pro settings. All right, make FPGA FPGA.QPF. All right, there we go. All right. All right, let's go ahead and open that up. All right, so for this one, I'm going to go in and we will configure, I think, let's see, what do we need? We need the reset release and need a PLL? Oh, no, I don't need a PLL because everything else is inside of that module. All right, so let's take a look at this. Interface protocols, Ethernet. Here we go, E-tile hard IP for Ethernet Intel FPGA IP. All right, let's go ahead and get this open and get this configured. This one's gonna be much simpler than the other one. Much less stuff needs to be connected for this to work. All right. But Quartus is still being slow. Great. Go figure. All right, well, while that's going, let's take a quick look at the documentation here. Let's see. Yeah, this one supports all sorts of fun features. It supports the IEEE 1588 time synchronization. Supports a bunch of other protocols. Okay, so PCS only is basically if you just want the PHY. It supports FlexE and OTN, and a bunch of other stuff. Custom PCS. I haven't played around too much with the various combinations that this supports. It also does like auto negotiation and things like that. Apparently, you can have it automatically figure out if it's on a 10G or a 25G or 100G link, and I don't know exactly how the reconfiguration works because I haven't played around with that yet. Let me put it this way. These cores are not quite as automated as you might think. Okay, so let's see. Single 10G link, that's fine. Single channel, yeah, I can't touch most of the stuff. So SyncE, not using that, and auto negotiation and link training, not using that. BTP, well, that's all off. Auto negotiation, not doing that. Okay, so enable native PHY debug master endpoint, that's important. Let's see. Yeah, I think I need both of these. Yeah, so I'm going to turn both of those on. All right, cool. So these are kind of a different level of debugging functionality here. The JTAG to Avalon Master and the Natify Debug Master, this allows Fortis to connect to basically the PHY and the E-Tile control registers. It's actually a pretty slick setup. I don't think there's really something equivalent with the Xilinx tools, at least not nearly as easy to use. So this allows you to go in and change settings, very easily from the tools when you're trying to, debug the links. All right, so select the rate. We're going to start at 10G. Yeah, so leaving these on means we can go in and poke at stuff from the tools. All right, so Mac and PCS, that's fine. All this is fine, I think. Bidirectional, CRC, okay. Okay, and we're going to run this with a 156 megahertz reference clock. All right, so we're going to need the adaptation soft IP, right? We're going to set this to 10G. Yep, okay. Go ahead and store that. That looks good. Okay, so the adaptation stuff is required to tune the DFE and whatnot in the actual serializers. This is in the receive direction to make sure you can get a sufficiently high signal integrity for the link to work. At higher speeds, it's more important, but even at 10G, it's important. Okay. All right, so that looks fine. I'm going to go ahead and generate this, and then we'll go ahead and instantiate in the Verilog and go from there. And so at some point, I'm going to have to figure out some of the more complicated features on the E-Tile. And for some of our experiments, you may actually end up running the E-Tile in PCS mode, or basically bypassing everything except the serializer. So at some point, I'll have to figure out how all that is going to have to work. But one step at a time. Start with 10G, get all the kinks worked out at 10G, and then move to a higher speed. Okay, cool, that's done. So I can go over here now. Here is the FPGA top level code. Now with this one, I've already configured the core code to remove the Ethernet MAC. So for the MX board, if you look at the core code, I have an Ethernet MAC here, right? 10G Ethernet MAC with built-in FIFO, because this is designed to connect to a PHY in the top level. Okay, but for this one, because the MAC is inside of the E-Tile, what I did is I removed the MAC and I replaced it with a TX FIFO and an RX FIFO. So now we just need to, do all the plumbing, as it were, to get everything connected. Okay, so here's the MAC IP. Go ahead and go into MAC inst. Going to ignore all those parameters and just use the defaults. Okay. Okay, this one has a fair number of signals here. But most of these signals can actually be ignored. Not all of them, but most of them. Okay. I need to do one other thing, actually. I need to generate the reset release IP. All right, so that's fine. This one is for, that's for the Mac. All right, so that one's been, okay, sorry, reset release. Okay, that's that. Go ahead and close this, because I think we're good to go on that. All right. Okay, that looks good. Go ahead and generate that. Excellent. All right, saved that. Yeah, the other advantage of the E-Tile is that it saves logic resources as well, because you don't have the actual Ethernet MAC in the FPGA, right? That lives in the tile. So ostensibly, that would also shorten the amount of time it takes to generate the code. Not strictly true, but Okay, let's go ahead and get some of this plumbed up. So the first thing I need to do is I need that reset release. component. So I'm going to go ahead and copy that from over here. So let's see, and init done, reset release, and I think I also have the same 100 megahertz clock. All right, let's go ahead and do that. I will go ahead and put that right there. The clock has a different name. It's this mouthful instead of that. All right, come on. All right, cool. There's the clock, and I have the reset. Logic is the same. All right. So now what I need to do is start making all of the internal connections here. So I need the TX PLL locked. Right, okay, so there's CDR lock. We don't really care too much about that because that's going to be handled internally, but we do need the PLL locked here. Mac TX PLL locked, because that's going to be used to generate a bunch of the reset signals. And let's see, then we have the reference clock. That's going to be coming straight from the top level here. I think I'm just using the first one, right? I said that was 156, so I'll just use that one. Okay. And then this passes through the clocks with a couple of different division factors. So the PLL is the clock that's derived from the input reference clock. And then the rec clock here is the recovered clock that's recovered from the incoming data. So because this is a Mac, it should be able to basically run everything in terms of the original transmit clock. So you actually don't need to have any async FIFOs after this necessarily, assuming you're running at the same frequency. All right, so I'm going to go ahead, wire Mac clock, wire Mac set. Okay. All right, so what we're going to do is we're going to take the 161 megahertz transmit clock and we're going to use that block most of the logic. The rest of these can be ignored. Okay, and then we need serial connections, right? So these are going to be the TX and RX connections up here, right? So I've got, let's see, it's going to be USFP0, TX, oops, is it not like that? Oh, QSFP1, okay, TXP0, okay. And I'm going to go ahead and place all of these with that, and then I will clean up. Oops. I want to delete the commas. All right. So these are the negative versions, right? And then I have RX and RX. All right, very cool. All right, so what else do we have here? So we have reconfiguration. So this is these are the ports that are connected to the transceivers, the control and status registers for the actual serializers. So if we go take a look at the E-tile, where was that block? Okay, here we go. So this is actually talking to the PMA components, the actual serializers. And then this Ethernet reconfig controller here, this one is talking to the Mac. So yeah, just to make things a little bit complicated. But there's a lot of stuff that can be ignored, like stat snapshot. I will just tie that off to 0, right? Simple. We don't need anything with that. IBER, I don't care about that. I'll come back to the reconfigured ones. TX lane stable, that's a status output that we don't care about. PCS ready, EHIP ready, RX block lock, alt status. Don't care about any of those. So SL, clock, EX, and RX. So SL is the actual Ethernet Mac portion of it. So this is going to be the Mac block that we're going to hook up to this guy here, right? So Mac block, okay, all right. And then we also need the TX and RX reset from the Mac. So these I'm just going to call Mac reset. And then I need to put in a reset controller here, another one of those. I have another reset here as well. Let's see. Okay, so I think all of these are the same. Yeah, okay. think that's right. Yeah. Okay. Let me go ahead and just add that reset controller real quick. I have this reset controller here, so I will just recycle that guy. All right. So this is going to be the Mac reset module here, and this is going to be in the Mac clock domain here, and this is going to be looking at RST 100 megahertz or not Mac TX PLL locked. So if the PLL is not locked, then you reset it. Or if we're getting a reset request in from, the rest of the system. Okay, so these, I think all three of these are just going to be hooked up to the reset line like so. Okay, the FIFO connections, I don't care about those. These could be useful information for certain things, but for what we're doing, that's not necessary. And down here, we got a bunch of pause. Okay, so this now is the Avalon streaming interface. Well, actually, except for that one. This is all Avalon streaming. And we got some more status and pause stuff. All right, so status, these are outputs there. Okay, this is transmit PFC. This is so PFC is priority flow control. These are for sending pause frames for specific traffic classes. So I'm not using that, so I'm going to turn that off. PX pause. Again, don't care about that. All right. All right, so this has pared that down quite a bit. I have a handful of signals left that need to be hooked up. All right, so this is going to be clock 100 megahertz. Going to be reset 100 megahertz. Okay, cool. That looks good. Now I have a bunch of these are memory mapped Avalon connectors that need to be tied off. So basically all the outputs can be ignored, all of the inputs be tied off for both of these here. All right, so output, and then all of these connected to, all of these need to be tied off to 0. Okay. Rid of all of these things. Okay, and then again over here. Okay, all right, so the last thing I need to do now is adapt between Avalon and AXI. So go ahead and take a look at this. I have all of these guys here, right? Okay, so I'm going to go ahead and create some signals for these. For all the streaming connections. All right, so I'm going to go ahead and make that Mac AVST. Okay, oops, fine, I'll get rid of all that. Actually, all right, so data is 64 bits, empty is 3, error is 6. Okay, so data are 64 bits. Empty, there's 2 empties, right? Yep, there we go. This was 3 bits. Okay, and then the error was 6 bits. All right, that looks good. Okay, there's that. All right, Quartus is still running for the other board. Okay. All right, so the next thing I need to do is put together some real simple logic to adapt this to AXI. And there's 2 things I need to do primarily. One of them is I need to reverse the bit order. I need to flip-flop between the empty and the T-keep signals, and then I need to regenerate the startup frame signal for the transmit direction. So that's not particularly really complicated. So let's take a look at this here. I'm going to go ahead and take all of these signals. All right. That down. We got wire. Okay, data 3 to 0. Keep is going to be 7 to 0. All right, this one is going to be 0, 7 to 0. Okay. And then I need all of. Okay, cool. So let's see, RX first. Oh, and then I also have, yeah, I have clock and reset. Okay, so this is coming from Mac clock, right? Mac reset. Okay, very cool. And again, same thing over here. Mac clock, Mac reset. Okay, excellent. All right. Data keep valid last user. All right, that looks good. Okay, and then I need to go ahead and all of these are going to be assigned based on Avalon streaming signals. So Avalon streaming and AXI streaming are pretty similar, except for a couple of important differences. Usually how things work, right? Okay. All right, so this is going to be the Mac RX data. Mac RX. Yeah, Mac BSTRX. STRX data. Okay. All right. So this, I'm gonna go ahead. This is going to be swapping bytes around. So I got to do all of the bytes separately. So this actually works. All right. Cool. So I do that. 2, 3, 4, 5, 6, 8. Oh boy. All right. Let's see here. 5 to 8. Remove all these here. All right. 55 to 48. 7, 40. 39 to 32, 1 to 24, 16, 8, 7 to 0. Okay, I gotta go the other way, right? All right, 15 to 8. All right, and 3 to 16, yada yada yada. 31 to 24, 39 to 32, great, 47 to 40, 55 to 48, and 63 to 56. Okay, so that byte reverses it. Because Avalon, for whatever reason, they like putting the first byte in the highest order bits just to be confusing. And then the tkeep here, this is going to be shifted by Mac BSTRX empty. Okay, so empty indicates kind of the number of byte lanes that don't contain any data. So we got to shift it so that works out correctly. Mac RX valid. Okay, and then we have Mac RX end of packet. And this one here is Mac RX error is not equal to 0. Okay, so in the transmit, or sorry, in the receive direction, I think that's all we need to do. Now in the transmit direction, it's similar. All right, so let's go ahead. I'm going to copy all of this and then reverse it, and I need to do a little bit of additional work here. All right, so the one thing is I need a register here. Okay, SFP1. I'm just going to. Okay, this is going to be frame reg. So this reg is set when you're in the middle of a frame somewhere, and we need that to properly regenerate the start of frame signal. Okay, so I flip all these to TX. Okay, RX, I didn't have a ready signal connected, so that's fine. Okay, cool. Now I go ahead and reverse all of these. Like that. Okay, that looks good. All right, so I have all the data lines, that's fine, except this one is not going to work. I need to do that differently. So assign Mac BSTTX empty. Let's see here. So if the highest bit is set, then I 0, right? Otherwise, I go to the next bit. Right. 6, 1, all right. Going into the last one. Cool. 6, all right. 5, one. Okay, and then the last one here. All right. Oh, these all need to be question marks. Yes. All right. Cool. I think that will work. And then the valid. That looks good. End of packet. Okay, but I also need to set start of packet. This is TX. Start of packet. Okay. So this one is going to be valid and not frame rig. Okay. That makes sense, right? Okay. And the TX error, get rid of that. Okay. Nice. And then I need one always block here to do the rest of the work. Okay. So this is if. I'm looking at tvalid and tready. All right, tvalid and tready. Set frame reg is going to be set to not of last. Okay, so if that makes sense. All right, one more thing here. If Mac reset, I need to make sure the frame reg it's set back to 0. Okay. Okay. That looks somewhat reasonable here, I think. Okay. Go ahead and make sure that looks good. All right. So let's go ahead and kick off Quartus for this guy, and hopefully it won't take all that long. All right, let's see. Probably have a syntax error somewhere. While this is running, we can take a look at the Ethernet specification as for what this stuff is going to look like on the wire. All right. Just making sure we don't have any syntax errors so far, which there's a pretty high probability of that. Oh, I also need to do one other thing. I forgot I need to connect, need to pass the clock through to the user logic. So here, sign, these are just going to be Mac clock. Okay. Was that the only weird thing? Oh, TX skip CRC. Yeah, okay. That's fine. Skip CRC, yeah, that was up here. I don't need that. Okay, cool. I think that was the only thing I needed to do. All right. Warnings can be useful. Oh, TX access. Oh, I need to also drive that. Okay, cool. Sign, oops. Sign USFP1 Mac TX access T ready int. That's going to be Mac AVST X TX ready. Okay, there we go. Okay. I think we're doing okay. I'm going to go ahead and start that off. Like there wasn't any syntax errors. I didn't add any syntax errors. I think we'll be okay. All right. So that's going to run. Once that's done, let's see about the MX one. That's still going. That could take a couple more minutes to finish up. All right. So once both of these are done, then we can see how it runs on the board. Let me make sure everything is set up in preparation for Stratix MX. Looks like the board's hooked up for that. All right, so as soon as that's done, we'll take a look. All right, in the meantime, we'll let that run. Oh, okay. It looks like the Stratix MX design is almost done here. Timing failed, which is expected because I didn't add any timing constraints for any of the async FIFOs anywhere. But that should not be the end of the world, I don't think. Hopefully that works out okay. All right. So this is going to generate the programming file. I'm going to go ahead and get the programmer started up. Let me get the board running. All right, board is going. Let me go ahead and get the programmer ready so that as soon as the programming file is done, then we can get that loaded on the board and see if it wants to bring up a link. Okay, let me put this away. Need that one. All right. I don't need that. All right, let me see. That is connected, so let me go ahead and run auto detect on there. If you haven't noticed, Quartus is a little bit slow. The other thing that I'm going to do here is I have a, oh, okay, let's see, we have, was it a -1? I think it's a -1, yeah. That should be right. Say what device? I think that's right, okay, yes. I don't think it makes that much difference at this point. Then it's going to ask again about the max 10. That one is irrelevant. Okay, there we go. All right. Okay, so we have the programming file. All right, so now I need to go ahead and set this up to load the file correctly. So I'm going to go ahead and change file, FPGA.sof. All right. So the sof, I guess, is kind of the Intel equivalent of the Xilinx bit file. I don't know much about the file format, but it serves kind of the same purpose. All right. Wait for this to finish loading. Gotta make sure that box is checked, and I can hit start. This goes ahead and programs. Okay, very cool. Now, what I need to do is check. I have a couple of these scripts that are already running. These are running inside of a NetNS shell, so they can only see the network interface on the computer that is connected to the board. Now, this says no carrier, so that means it did not successfully bring up the link. All right, so now let's figure out what's going on. So I'm going to go ahead and pull up the signal tap, and I think there's a refresh button around here somewhere. Setup, right? Okay, I select that. Okay, okay, there we go. All right, so this has figured itself out, I think. So let's take a look. If I run this, what this looks like. Okay, so I have a capture, and something is not happy. It's continuously bit slipping. Hang on, I'm going to try a different NIC on here. It's possible that the Mellanox NIC that I have is causing trouble. I'm going to hook up an Intel 10G NIC, and we'll see if this is a little bit better behaved. So the main thing that I'm looking at here is the fact that this bit slip signal is toggling. So that means that the PHY is trying to lock, and it keeps slipping to a different bit position in the serializer, but it can't find the signal that it can't find the pattern that it's looking for. We'll take a look at the Ethernet specification, and I'll explain how the locking works in a minute. But let me switch this over to a different NIC. Hopefully, it'll be able to lock. All right, that should be hooked up. Let me rerun this, and we'll see what it looks like. All right, that's not a good sign. last time I tried this, it was at least able to lock. I don't know why this is being so annoying. Well, let's see here. The RX data from the series is coming in as all zeros. That doesn't make any sense. Let me try the other one here. The port. Okay, so with the other port selected, okay. Well, obviously I fouled something up. Let me take a look at the code real quick here. I was hoping to show what was going on at the link layer while this thing was trying to lock, but obviously I screwed something else. Obviously I screwed something up. I'm not sure what though. Well, let's take a look on the TX side real quick here, and we'll see what that looks like. Just to make sure this is sensible. Go ahead and run that. Single shot capture. Okay, so on the TX side things look fine, right? So on the XGMI interface, when nothing is happening on the link, but it's not actually sending data, it's continuously sending idles. So this is sending 07070707, which are 8 idle control characters. All locations are marked as control characters. The PHY then encodes it with block type 1E, and there's the header, right? And then it gets scrambled, and that's what actually gets sent out over the wire, right? The CEF, whatever. This is the scrambled stuff that gets sent out over the link. Okay, but the question is, what is going on the receive side? Obviously, something is not happy. The problem is that I'm not sure what it is at the moment. So the module, it was released from reset. The transmit side is running. The ref clock is hooked up. TX and RX, those are connected. Lock to ref, lock to data, that's right. TX core clock in, right, RX core clock in, that looks fine. TX parallel data, yep, okay, that looks fine. Data valid, TX parallel data, yeah, okay. Let me make sure I have all these signals named correctly, I think so. TX header, TX data, RX header, RX data. Presumably those are also correct. Yeah, okay. Yeah, so in the receive direction, I would expect to be seeing in this signal something that looked similar to signal we were looking at previously. Unless this is, and I'm only seeing the lowest couple of bits changing. So did I? Oh man. Well, okay. All right. That's not so great. Okay. Well, okay. So let me put it this way. I was planning on rerunning this a second time anyway, because the bit ordering is different from what I expected. So I will fix that issue, and then I will also go ahead and flip bit reverse, and we will rerun the tools. All right. At least that was a very stupid mistake, but at least it was a simple mistake. All right. I'm going to go ahead and restart this. Oops, this one. And when that's done, we will take another look at the result. All right. Go ahead and save that. All right, cool. Okay, so in the meantime, while both of these are running, I will go ahead and we'll take a look at the Ethernet specification for what is going on the wire when 10G Ethernet is running. So the thing to keep in mind with Ethernet is there's a whole bunch of different variations. Let's see, I think the original version of 10G was this thing called 10G base X. And this is not what we're implementing now. Need to take a look at this and make sure this is, yeah, okay, yeah. So as Ethernet was developed, they started doing stuff over fiber. And one of the first fiber, maybe not the first one, but one of them was called an SFP module that runs at a gigabit per second. Then they said, okay, we need a faster version, and they came up with a QSFP, not a QSFP plus, but a QSFP. And this one runs a little bit faster. It has 4 lanes. It's kind of 4 SFPs in one, and it runs those 4 lanes at 3.125 gigabits per second. Right. So let me pull up IPython here so we can do some math. So 3.125. Hang on, I wanted IPython, not Python. Okay. All right, so 10G is the data rate, but it's 8p10b encoded, right? So we got to multiply by 10 over 8. That gets the raw data rate, and then you divide that across 4 lanes. You get 3.125 gigabits per second per lane. So that is what was used for this 10G base X, and it's basically the same as kind of gigabit Ethernet over fiber. It uses, as far as I'm aware, the same kind of encoding scheme, uses the same control characters and whatnot, but it stripes everything across 4 lanes running at 3.125 gigabits per second. And this, even though this is not really used anymore, this informs kind of how the rest of the high-speed interfaces work, because 10G base X is what defined XGMII. So you remember in the Verilog here for the MX, we have the TXD and the TXC signals, right? So for XGMII, the TXD and RXD carry, byte lanes of data. XGMII is defined as being a dual data rate interface, but in a lot of cases it's unwrapped and sent as a single 64-bit interface at 1/8 of the clock speed, right? Instead of a quarter. Yeah. So in this case, this is for the dual data rate one. So we have 4 lanes, right? This is 0 through 7, 15 through 8, so on and so forth. Each one of these then corresponds to 1 bit in the TXC in this associated signal. So that you got the TXD and the TXC in the transmit direction, and the RXD and RXC in the other direction. And then somewhere the symbols are the control characters and whatnot are all defined. Yeah, here we go. Here's the XGMII table that defines all the control characters. Let's see. So there's 2 different ones here. So this is the PCS code group mapping. Wait, why are there 2 different tables? Oh, this is for TX, this is for RX. Okay. I thought they were the same. Are they not the same? They look the same to me. Okay. So if the TXC is 0, then the data lines, the TXD or RXD carries data directly. Or if it's 8p10b encoded, it uses the D characters. LPI, which is what they call low power idle, it puts this bit high, so indicating it's a control character, and then it sends 6. Idle, it sends 7. I guess there's 2 different, idle in I, idle in T. I would need to check what that refers to. And then there are some kind of out-of-band control characters as well. So there's a sequence, an ordered sequence control character as well. And then there are framing control characters. So start, terminate, and error. So whenever you send a frame, let's see here. What you do is you send a start control character, and then you send the packet payload data, and then a terminate control character. And the start control characters are always sent in lane 0. So start, data, terminate, and then everything that's not corresponding to a packet is idle. And then when it's sent over the link, then these will get encoded with the, the 8-bit, 10-bit control characters and sent that way. For 10G base X. Now, most everybody these days uses something called 10G base R, which uses a single transmit pair and a different encoding scheme called 64B, 66B. So with this setup, what we actually do is we take 8 control characters and we pack them into these 66-bit blocks. And this table here describes how that works. So in this case, we have bit 0 through 66. And then depending on the sync header that's attached, either 01 or 10. If it's 01, then we send 8 data bytes. If it's 10, then we send one of these other block types, right? So in this case, this block type 1E is 8 control characters. And the control characters use a different encoding. So they have this other table here, which relates the XGMII control characters to the 10G base R. So previously, when we were sending idle, we would send, 7 on XGMII. I can go ahead and pull this up in the transmit direction anyway. Here are the idle control characters. So we've got 8 control characters, all 8 bits in TXT are set, indicating that they're all control characters. And then the encoded data, it's encoded as block type 1E. Block type 1E corresponds to 7 control characters, or 8 control characters. And idle is encoded as 0, so it's all 0. And then 1, because this is block type 1. The block type 1. Should be block type 1, yeah. yeah. These are all block type 1. This table is rather annoying actually for a couple of different reasons. The problem with this table is that it's listed in transmission order, so it's left to right in transmission order, but it's sent LSB first. So that means all of the numbers are, kind of in some sense backwards from what you might expect from kind of the traditional way that you write stuff out. And this wasn't really spelled out anywhere that I could find in the spec. I actually had to pull out the, I was building my PHY module in the first place. I actually had to fire up the ILA in Vivado to figure out what the heck the bit order was supposed to be for all of these data bytes. And the other thing that was kind of complicating that is, for whatever reason, it seems like the Xilinx transceivers are set up to transfer this bit reversed. So this would be bit 65, 64, all the way down to bit 0 here. So yeah, it's kind of confusing. Probably the more annoying thing about this table is that this talks about some of the sync header types in the hex, or in the text. Sorry, in the text. So where was that? There's some. Okay, so here we go. The sync header is 01 for data blocks. So you would think, okay, 01, that must be just decimal value 1, right? You go look down here, 01. Except the sync header indices are reversed, right? This is the least significant bit. This is the most significant bit. So this is actually, this actually has value 2, which is kind of a head scratcher. And the real head scratcher here is the block type field, right? Or some of these other fields, because they have an indication here. For example, the block type 1E is sent as 011111000, right? And this is kind of backwards to what you would expect. So I guess in this case it is actually consistent with the table, but this is backwards from what you would expect. If you write this out in binary, you would write it as, this is 1, so it's 0001, and then E is 1110. You would write it out backwards from what this is. So yeah, I don't know why they do it that way, but this just ends up being incredibly confusing. If you took the whole table and flipped it left to right, it would make a lot more sense. Anyway, this one defines all those control characters, and the thing with the 10G base R is you actually cannot encode every possible combination of control characters. And the reason for that is that how these block type code works. So actually, the start and terminate control characters are defined by the block type field here. So this defines the start in lane 4, start in lane 4, start in lane 0, and then these characters here define terminate in 0, 1, 2, 3, 4, 5, 6, 7, right? So these are all the terminate in all the various lanes. So this is terminate in lane 0 with no data, terminate in lane 1 with 1 byte of data, terminate in lane 2 with 2 bytes of data, so on and so forth. So the start and the terminate are implied by the block type field. And you'll notice that there are actually there's actually three characters that define the start control code, right? And the ones you're mostly going to use are this one and that one. So this does complicate things a little bit from the PHY layer and from the Mac layer, because there's two possible positions where you can start the frame, either in lane 0 or in lane 4 if you unwrap it. And the reason they do that is to enforce the interframe gap in between packets. Yeah, so let's see. Once this thing finishes, then we can actually take a look at what the encoded frames look like on the wire, and we'll see what this looks like. Yeah. But I mean, so far, being able to find the particular bug here does show that these debugging tools are, rather useful for being able to get a view into what's going on inside of the FPGA that you might not be able to get otherwise, or that would be much more difficult to get otherwise. All right, let's see. So let's see, the DX one, that's almost done with the fitter. MX one is going to take a little while. All right, that's fine. Let's see, what else can we look at? I guess one thing that I could do is pull up. Actually, so I guess one thing that we did do is we took a look at the schematic of the MX board. While we're waiting for this, we can take a quick peek at what's going on the DX dev board. Right, so this one is kind of similar. I think, yeah, this one is 70 pages, this has 69 pages, so yeah. Both boards have a lot of parts. Now, on this guy, I think we actually have a few more peripherals, right? Because more of the tiles are connected. So this FPGA here, it has 5 tiles. It has 1 E tile that's hooked up to the 2 QSFPs, and it has 4 of the P tiles that are hooked up to PCI Express. Well, PCI Express and UPI. So this one here is hooked up to PCI Express. The other ones are hooked up to those UPI connectors. And let's see, with the P tiles, these guys support PCI Express Gen 4 and a bunch of other fun stuff. So this one will do PCIe Gen 4 by 16, which is a heck of a lot of bandwidth. And I think you can also bifurcate them. You can do root port, you can do endpoint. There's a bunch of stuff that you can do. But for today, like I said, we're going to be looking at the E tiles. We have the flow running for that. All right. As soon as that's done, hopefully it won't be that much longer, we'll be able to pull that up and test it out. Okay. The thing with the E tiles is there's a couple of different configurations that they support for the actual serializers. So let me see if there's a better diagram in here. The serializers that can be run in either PAM4 mode or NRZ mode, and there are some restrictions, complicate things a little bit if you're going to use them in PAM4 mode. I'm trying to remember where it discusses that in the manual here. Channel placement. Okay, here we go. This talks about things a little bit in more detail. Can I zoom in here? All right, there we go. Okay, so this is a plan of what is going on the E tile. So this is the channel settings, and this is the floor plan. So these are all of the interfaces to the FPGA over the EMIB link. These are EHIP lanes so that connect to right, these are for either the 10G or the 25G MACs. So each EHIP lane is one 10G 25G MAC, and then each EHIP core is one 100G MAC. And then you have the RS-FEC blocks and then the channels. These are the PMA channels, the actual serializers. Right, so each one of these is capable of running at 10 gigabits or 25 gigabits or basically 25 gigabaud PAM4, which is like 50 some odd gigabits per second. But when you run them in PAM4 mode, you actually cannot use the adjacent channels. You have to skip channels. So this diagram actually shows a whole bunch of different stuff that's configured. So these first 6 channels are all configured to run at 25 gigabits per second. So there are 6 of these 25 gig MACs that are used. Both, it uses half of this RS-FEC block and this whole RS-FEC block plus 6 transceiver channels here. That's pretty straightforward. And then there's 2 more channels that are set up here that use, well, I guess these do not use the RS-FEC block, so it skips over those. These 4 channels are then set up for 100 gig, so you've got 4 interfaces that use the AIB and EMIB connections to the FPGA. Then they use the EHIP core for the 100 gig MAC, and then the RS-FEC module, and then 4 lanes. This one here shows a setup with PTP enabled. So with PTP, you have to transfer these timestamps, and the timestamps are very wide. There's something like 80 bits, I think. So in order to transfer those, it actually uses several additional interfaces through the AIB and EMIB connections to the core, so or to the FPGA fabric. So when you turn on PTP, you actually lose a couple of these inner lanes. And unfortunately, you don't have much control over that. So when you lose these inner lanes, then you actually lose these channels as well. So, I mean, I guess you might be able to use it as a PLL or something, but you don't have the data path connection, which can potentially be a problem depending on what you're doing. So these have, so this example here shows setup with PTP enabled for 100 gigabits per second. I think if you're using 10 gig and 25 gig, it still uses these, but these end up being shared across all the MACs, and I think there's probably soft logic to do the right thing with the timestamps that are coming across the link. This top setup here shows a not RS-FEC, a PAM4 setup. This is a 100 gig PAM4 with 2 channels, and this uses, you know, like I said, you have to skip channels when you're using it in PAM4 mode. So in this case, that's how it's wired up. So the issue is that with the QSFP modules, if you want to use them in PAM4, you got to use channels 0 and 1. You actually can't skip a channel on the actual QSFP transceivers. So when they wire it up on the board, they actually have to crisscross those channels. See if I can find that section of the data sheet here. Here's a UPI links. Okay, here's the QSFP controller. Okay, here we go. Here's one of them. So we can see TX1, TX2, TX3, TX4, and here's P0, P1, P2, P3. So they crisscross these two, as you can see. So if you're using every other channel for PAM4, then you can still actually support using this thing in PAM4 correctly. This is something to be aware of, because if you want to run this at 10G mode or 25G, the lane ordering is maybe not what you expect it to be. So you might need to, you know, sort that out in the soft logic. But yeah, it's the kind of stuff that you have to look at when you're laying out the board for some of this stuff. Okay, so the DX design, that just finished. I'm going to go ahead and get the board set up, and we'll see if it works. One moment here. Okay. There is the DX board running, all powered on. Now let's see if I can go ahead and load that. All right. Let me go ahead and fire up the programmer. The other thing I need to do as well is pull up. Well, this is a different interface. So this is going to be using this guy. Auto detect. All right. Go ahead, restart my scripts here. So the main reason I use these scripts is because the design by default listens at a fixed address. So if I use these netns scripts that I have, it prevents any address conflicts with my local network. Otherwise, I got to make sure, you know, nobody's using that address or something, and having two NICs that see the same, you know, address space kind of cause trouble sometimes. So let's see here. It'll take a second to get itself figured out, right? This is currently reporting that the link is down, as expected. Okay, oops, programmer, there it is, okay. I'm gonna go ahead and configure that guy, hit start. Programs it, and I got no link. Dang, 0 for 2, all right. Let me go ahead and take a look at some of the other transceiver debugging tools that we have here. That was the idea today, to take a look at some of the debugging tools. So for the E-Tile, we're going to use something called the system console. So I'm going to go ahead and fire this up, and we'll take a look. So this one can communicate with various debug components over the board, or over JTAG. So this will take a second to start up. Using this, we can take a look at what's going on the other end of the link, basically. All right, so what do we got? We got the Mac, and we got the, it looks like the PHYs. All right, so I'll start by opening up the Mac component, E-Tile Hard IP Toolkit. Okay, so this gives you a whole bunch of stuff that you can look at here. Okay, go ahead and start reading all statuses. Okay, so this is reading the status. We got the TX clock 161, RX clock 161. I mean, that seems fine. IBER, well, that's not so great. Okay. Actually do something here real quick. I'm gonna do watch. So let's see if anything changes. Okay, so I'm gonna go ahead and enable the loopback. Oh, that's interesting. I put it in loopback mode and the link came up. Huh. What is going on there? If I turn the loopback off, it goes down. One thing that happens with some Ethernet Macs and or PHYs is that they will kind of forward some link status information. So if the RX link isn't working, then it will report on the transmit side, you know, local fault basically. And what I think is happening is that since the receive side on the board doesn't seem to have, you know, figured itself out, it's reporting a local fault, and then the NIC is reporting that the link is down, which, I mean, I guess it makes sense, but it would be nice if it would, you know, differentiate between that. Okay, you know, local fault versus, you know, nothing. Okay, so let's take a look then at what else this supports. Let me do a system reset. Does that do anything? Still says no carrier. Okay, I think what I need to do, actually, let's take a look at the PMA adaptation here. If I select 10G NRZ and I hit apply, oh, link came up. Interesting. What is going on there? All right, let's see if this actually worked here. Let's see. So I do NC C-U 8. Okay. What? Oh. My. Okay. IP ADDR add 11199 for dev. Okay. Hey, it works. Okay. Boom. All right. So this is actually working, but for some reason we have to kick the transceivers to make it work. Interesting. I couldn't figure out why that was, so I actually went and I asked about it on the Intel forums a while ago. I was working on this a couple of months ago, trying to bring the link up, and I couldn't figure out why the link wasn't working. It's like it wasn't working, and I could, going in through the system console, I could, you know, kick it and make it work. But you know, these e-tiles are pretty advanced. They're supposed to be able to, at least I would assume, figure this stuff out. But apparently that's not the case. And this guy pointed me at some of the transceiver documentation, and specifically pointed me at the e-tile transceiver PHY user guide, which talks about how you trigger the adaptation controller on the transceiver. And what you actually have to do is go in over the transceiver reconfiguration interface and poke at some registers. And when you poke at these registers, it will load all of the adaptation coefficients and place the transceivers into the proper mode where they do the automatic adaptation. So I had to sit down and write a relatively complicated, actually it's not too bad, but it's a good handful of lines that performs the equalization, or it doesn't perform the equalization. It places the transceivers in the correct mode, and it's basically, you follow the instructions, right? You write this byte to this address, you read this other address until you get a certain value. But the one annoying thing is that they don't tell you what to wait for, right? You know, are you supposed to wait until this thing comes out of reset? Are you supposed to wait until you get a specific, until you see a specific value in a specific register? It's kind of unclear. So the code that I have is a little bit naughty because it just waits like, you know, 65,000 clock cycles and then just runs the sequence. I don't know if that's right, and it's definitely, if something resets the transceiver, then this will have to be rerun. So it's, to be honest, it's I'm not particularly happy about it. I would like to do something a little bit more intelligent, but if that's the only way to go, then that's the only way to go. So let's go ahead and incorporate that code real quick here. Oh, actually, we'll come back to that in a second. The MX board just finished. Okay, here is the Stratix 10 MX. I'm going to go flip-flop the board back, and we're going to run the MX code again and see if we get a link this time. And maybe we'll flip-flop back to the DX. Done with the DX for now, though, so I'll go ahead and pack that up. Actually, let me see. Where did that system console go? Yeah, I'm going to go ahead and close this. Okay, cool. Let's take a look. MX, give me a second. I'm going to get the board swapped back. All right, there we go. That board is up and running again. So let's go ahead and pull up the programmer. Here's the MX programmer. So I'm going to go ahead and start that. Kick that off. All right, that runs. Bink. Okay. Now the question is, did we get a link? All right, I got too much stuff open. Oh, we have a link. That's good. Does it work? Oh, man. No good. Didn't work. Okay. Let's see if we can figure out what's going on here. Scan chain. All right. Ready to acquire. All right. So let's take a look at the RX side of things and we'll see what this looks like. Something is not happy. So the TX side is working, but the RX side is is not happy. What is going on here then? I screw up the bit slip connection this time. Well, that's not what I was expecting. I was expecting this to at least get block lock. Unless it did get block lock. Hang on a second. Let me zoom out. I'm wondering if I have something configured incorrectly with the transceiver. I'll have to go take a look at that then. Well, we might not be able to get this one working today. That's really annoying. Well, okay, so in this case, at least we are seeing the full set of data on the RX data side, so that's good. But it's not. It doesn't actually end up getting the proper alignment. What could be going on with that? Yeah, I don't know if there's much I can do about this. Dang it. Take a quick look and see if I screwed something up in the transceiver configuration. Yeah, this one might be a lost cause. Let me put it this way. I do have it working in a different project, but I probably made a configuration mistake here somewhere that's preventing it from working. Because I should be able to get block lock, even if there's something else wrong. I guess I could talk about block lock real quick, and how it's supposed to work, and why it's. I'm not going to be able to tell you why it's not working right now. Let's see. There should be a block diagram, or not a block diagram, a state diagram in here somewhere for getting block lock. Lock state diagram. This one. Okay. So this is how things are supposed to work. It's just about as simple as you might think. When this starts, it starts out with this shift count. Well, let's see, is sh count, test sh. I'm trying to remember what all these variables are. It's been a while since I looked at this. But basically, the way it works is you get data, right? You get a new 66-bit block. You check to see if you have a valid header. Right, so this is sh is sync header. That's right. So sh count, sh invalid count, slip done. Okay, so sh valid, sh not valid. Okay, so you test the sync header and you see if it's valid or not. If it is valid, you increment the number of valid sync headers that you've seen. Otherwise, you increment your So sh count is the number of headers that you've seen. Sh invalid count is the number of invalid headers that you've seen. Okay, so if you see a valid one, then basically if you've seen a sufficient number of headers and you haven't seen an invalid one, then you have lock. Otherwise, if you see then you basically have to loop back and check more. Either you loop back here or you loop back here. You loop back here if you haven't seen enough, or you loop back here if you've seen some invalid ones. Yeah, okay. If it's not valid, then what you do is, well, it depends on if you're locked or not. If you are not yet locked, what you will do is you will go to the bit slip state, where you will slip by one state, and then you will be checking based on the subsequent bit position, and you keep doing that until you achieve block lock. Ostensibly. If you don't get block lock, well, then things don't work. All right. So the question here is, did I forget to check a box somewhere? I thought I checked both of these. RX data bit slip, yes. RX bit slip. Okay. Yeah, okay. That's very strange. That's 64, that's 66, that seems fine. Low latency, no. Don't care about interlacking. Hmm. Well, that's a pain. All right, so I'm not going to be able to figure this one out on the stream. Obviously, I screwed up somewhere in terms of something. I'm not sure what's going on here. But at least we have some visibility in here where we can see what's going on at the physical layer and have some idea of where to look. So, you know, it's not working. Interestingly enough, the transmit side does seem to be working. So the only thing that we changed there, right, so previously it wasn't coming up, this time it is coming up. So that means that that we now have the bit ordering correct, because last time we weren't getting a link, we are getting a link now. So the bit ordering is correct, but there's something else that's causing trouble. Dang, I'm like seriously annoyed about this because I thought I had this all sorted out. Yeah, so this should be high cycles, low cycles, 32. That should be right. All right. Well, I don't think there's much else that I can do on the stream today. I do have, let's see. I could kick off the DX with the transceiver control state machine. But that would just take another half an hour. Let me see here. I'll just go ahead and do that, and we'll let that go. Let's see. So I need to do, for that, I need a new file. I'm not going to type this whole thing in. I'll just paste it in here. Okay. So this is a state machine that talks to the E-tile on the Stratix 10 DX. And the idea with this is it goes through and carries out all of the operations that are listed. Let's see, where was that? That are listed here, right? It goes through 40143, 40144, 200, 201, 202, 203, 207. Does that twice. So yeah, we've got 40143, 4144, you know, all of those addresses are in here. This goes through, it waits for a PL to lock, it loads a PMA configuration, and then it sits on here and it reads the status register until it gets the value it's looking for. And then it starts the initial adaptation. It has to write 4 registers in sequence for that, and then it has to wait for this status bit to get set correctly. And then it does the same thing again. And when it's done there, then it goes back to idle basically. So it does that, and then there is some additional logic for properly interfacing with the Avalon memory mapped interfaces, as well as some additional code for inserting delays as necessary. When this thing comes out of reset, it waits for, you know, a while, what, 65,000 clock cycles before running the sequence. It would be nice if there was a another technique for triggering that, but all of my reading over the data sheets, I have not been able to figure out what the most appropriate method would be for doing that. All right, so I go ahead and instantiate that, and then this gets connected to the transceiver reconfiguration interface here. So I take all of these, right, and then it goes to reconfiguration address. Yep, okay. All right, we delete these zeros. All right, so that goes here. I need to add that to the project, and then I can start it up again. I'll take a couple more minutes and see if I can figure out what might be going on with the MX design. That seems really weird. All right, add files. Yeah, this is a DX design. So all right, so I'm going to go here, go up, RTL, receiver control. All right. Cool. All right, so that's going to run. Let me see if I can make heads or tails of what's going on with the other one. If I can't figure it out, I can't figure it out. There is one issue that I am aware of that I was going to try and find, but I would only be able to find it if it was actually able to achieve block lock. The question is, why is it not achieving block lock? See if I can take a look at the current version of the code that I have and see if the problem is on the transceiver side or something else. Let's see, where would that be? That was here. Stratix 10 MX. Yes. Okay, so let's see. I think I have the bit slip timings correct. I put those in here. Okay. No, I put it all the way in here. Okay. Bit slip timings. Yep, 32 high, 32 low. All right, so that's fine. That's not an issue. RX clock 1 int. RX clock 1 int is the RX clock out, RX core clock in, RX clock 1. That looks fine. RX is locked to ref. I don't have anything connected there. That's fine. Serial clock, QSFP0, cal busy. All of these are fine. Data header. Okay, that's fine. That's 1, that's 0. Yes, that's bit slip. Yes, okay. And that should be coming directly from the bit slip there. If it's not bit slipping, then that would explain why it's not working, but that doesn't seem to be the case. So it is connected to the transceiver. Okay. RX and TX clocks connected here. TX and RX, well, that would give sort of an error if that was connected wrong. Data RX header, that seems fine. All that's not connected. All right, well, the bug that I was going to try to find, so here's what I'm going to do. I'm going to copy over a known good transceiver configuration IP file. Because I guess I must have screwed something up in there somewhere. Let's see, Stratix 10 MX. Oh, what was I looking at? This one, yes. Yes, okay, Stratix 10 MX, go into IP. I need the transceiver. Oh, these are fine. I'm going to go into here and IP receiver. Okay, very good. Is EX. So I'm going to go into the MX. All right, let me go ahead and replace that. Okay. That one's a lot bigger. Interesting. Oops. Place. Not, place. Okay, there we go. There we go. Okay, so the issue that I was going to try and debug, but apparently I must have screwed something up with the configuration, so something else is wrong. But when I did the bit reverse in the PHY, the problem is that I'm looking at the sync header basically at the wrong end of the register. So let me go back to that table. All right, so this table here is kind of showing what's going on in terms of what gets sent over the link, right? So it gets sent LSB first. So the idea is you get a sync header and then you get all of the data. Now, coming out of the interface on some FPGAs, this comes out in bit 66, and this comes out in bit 0. In other devices, this is reversed. But the thing that makes this slightly complicated is because sometimes you get the sync header on a separate port. So I have one port for the sync header, and I have one port for the rest of the data. And that's how things are set up here, right? Because I have a separate port for the data and for the sync header. All right, so it appears to me that if you turn on all of this standard 10G components inside of the E-Tile, the standard hard IP core components, it comes out in this standard kind of bit reversed format. So bit 66 would be over here and bit 0 would be over here. Well, sort of. You have, because you still have these two different interfaces, but it kind of assumes that bit ordering. I don't know exactly where that bit reversal takes place. I'm assuming that it's either in, let's see, where was that block diagram I was looking at earlier? Was it this one? I want to look at the enhanced. Yes, there we go. Yes, this one. Okay. So on the receive path, you have the gearbox, and then you also have a descrambler and the 6466 decoder. So I think one of these also performs the bit reversal. I'm not sure because the documentation actually doesn't say anything anywhere about bit reversal. Anywhere. I've looked into this. Because last time I ran into this problem, I was banging my head against the wall for quite a while, trying to figure out what happened and if there was a box I needed to check or something else. But one of these, I believe, does the bit reversal. And as part of that, it gets the sync header back in the right spot and basically, you know, unwinds everything that needs to be done so that everything works. Problem is, apparently, if you turn on the gearbox, but you don't turn on these other modules, you basically don't get that bit reversal. But for whatever reason, it's still pulling this sync header from the same end of the register. So basically, what ends up happening is that I get the sync header bits, 1, 0, and then I get the payload. Well, hang on a second. Basically, it's taking the sync from the wrong end of the register. And as a result, if you block lock on that sync header, it's basically attached to the wrong data block, right? It's attached to either the data block right beforehand instead of the one afterwards. And that's an issue. So what I need to do is basically reshuffle that so that the sync header ends up on the correct end. All right, so let me remember how I did that real quick. I guess this code that I'm looking at here is the old version. All right, so what I'm going to do is I'm going to make a copy of this here. Make these, call these phi. Okay, and I'm going to go down here. I'm going to call these phi. All right, so that's that. See here. Then I need to do another little assignment here to flip these back into the correct order. All right, let's see here. So I need to do assign. Doesn't really make too much difference exactly how I do this. So in the transmit direction, I want to assign guys TX data and the TX header for this guy. Okay. I want to set that equal to same thing from the phi. So I'm going to take the header first and then data second. So this goes ahead and moves those bits back around to where they need to be, basically. So after you do this, then the data should be in the proper alignment. And hopefully once this is regenerated with the correct settings, then things will work. Okay. Right, so transceiver TX header and data. Oh, okay. I guess I did this the other way around previously. I'll swap these around. Header, data, header. Okay. Okay, let's. Okay. All right. I will try this one more time. If it works, it works. If it doesn't work, it doesn't work. Okay. I got a question here on the PCIe side of things. The PCIe side of things is a little different on Intel versus Xilinx. Is that part already covered in the projects? The answer to that is I'm working on it, basically. I guess I can spend a few minutes talking about PCIe while this stuff is running. So the PCIe situation is slightly annoying because it seems like every PCIe hard IP core kind of has their own idea in terms of what the interface should look like. So I guess I can pull up some documents here and we can take a look at what a couple different devices look like real quick in order to kill a few minutes. Let's see. So I will pull up, how about let's see, I need Altera, right? Why am I not seeing this? Okay, there we go. Altera tile. I want to take a look at the P-tile. Tile AVST, yeah, P-tile AVST 20.4. That looks good. Okay. So this is the P-tile manual here for PCI Express. This is the one that does your Gen 4x16. And somewhere in here they have a description of the streaming interface. Okay. Well, all right. Where is that? Okay, this talks about the streaming interface in a little bit more detail. So we got that, and then I'm also going to go ahead and pull up the Xilinx ultrascale documentation here for the PCI Express IP core on those devices. Okay, there we go. All right, so let's take a look at this here. Starting with the core, where does it talk about the, oh, here we go. Here we go. 512-bit. Sure, why not the requester interface? Why not? Okay, so the interfaces on some of these devices can be quite different, shall we say. Okay, so on the Xilinx ones, the way they have it set up is they have a single streaming interface for TX and a streaming, actually no, sorry. They have 4 streaming interfaces. 2 of them for the requester interface and 2 of them for the completer interface. So basically, they're kind of separating out TLPs based on the role that the logic is playing in the device. So the completer interface is for handling memory read and write requests that come in over the network, or not over the network, that come in from other devices. And then the requester interface is for the FPGA to issue read and write operations. And the advantage of separating that is that you're probably going to be using different components on the FPGA anyway for these guys, right? So you're going to have like a DMA engine that's going to be issuing requests on the requester interface, and then you're going to have like, you know, some sort of maybe memory interface on the or register interface on the completer side. So by putting this in the hard IP, this gives you kind of 2 advantages. One of them is that you don't need to do the demuxing yourself, the muxing and the demuxing yourself, but it also allows the requester and the completer to have separate backpressure paths. So if things get, you know, hung up on one side, then data will keep flowing on the other side. But another thing that Xilinx does that's kind of annoying is they actually have, they don't use standard TLP headers on their packets. They have their own kind of cooked up descriptor format. And there are some advantages to this, but the main disadvantage is that it's not a standard PCIe TLP header. So, you know, in this case, we have so with TLPs, they have to carry an address field, you know, for read and write requests. And the standard TLP, you actually change the size of the header based on the size of the address. So if it's a 32-bit address, you just send 32 bits for the address. If you need more than 32 bits, then you send a 64-bit address. And that in principle might not seem like that big of a deal, but it means that the payload data in the packet actually has to get shifted by 4 bytes depending on the size of the address, which is a little bit annoying. For the Xilinx ones, instead of doing that, they just always send a 64-bit address. So, you know, it is what it is. For a lot of other devices, they will use just standard TLP headers. Simple, straightforward, gets the job done. And, you know, somewhat more standardized because, you know, it's PCI Express. You kind of know what to expect when you're talking about TLPs. But something like the Intel P-Tile, they actually ended up using a very different interface. And the first time I saw this, I was like, oh God, why did they do something completely different? I mean, this is just a pain. But finally, I realized that actually this setup is really nice for a couple of reasons. So what they have on the P-Tile is instead of having a single data interface, they actually have, can I zoom in on this a little bit? There we go. They actually have 3 signals here. They have data, header, and TLP prefix. And the great thing about that is that if you add or remove a TLP prefix or you change the size of the header, you're not touching the data because they're moved over a separate channel. So one, this means that the size of the TLP header now doesn't really make much difference. Just in terms of, you know, where the data is aligned. You don't need to look at the size of the header to figure out how to barrel shift the data. That simplifies logic a little bit. And it also makes the header parsing logic easier because the header is always going to come out of this header interface at the same position. And you're never going to get data over there. And you're never going to get header over here. So it kind of simplifies some of the connections. And it also has the effect of kind of widening the interface a little bit because you have an additional 128 bits just for moving the header. And that's rather important when you're trying to run at, you know, Gen 4 speeds where it's like, you know, 256 gigabits per second. You're going to have a hard time dealing with all that data. So if you peel off the header separately, then maybe you can run at a slightly lower clock speed and still get a sufficiently high throughput. The other advantage to doing this is maybe a little bit clearer from some of these pictures, is that they actually have different endianness on these different interfaces. And at first I'm like, why are you doing that? But then I realized that actually PCI Express, the headers are big endian, and it's always easier to deal with data in little endian. So with this setup, you can keep the data in little endian, which makes things much easier for dealing with in the core logic. But then the headers are transferred in big endian, so everything always lines up the same way. So in this case, when you change the size of the header, well, the header always starts here, and then it's either a question of whether you have this, you know, last D word containing the rest of the header. So, you know, it's not too bad. So what I'm working on in the PCI Express side of things is basically converting the DMA engine and some of the other PCI Express components to speak something very similar to this P-Tile interface. And then on all of the other components, including the Xilinx UltraScale, as well as P-Tile and the Stratix 10 MX, which has the H-Tile, I'm just going to basically have to write adaptation logic to convert whatever that particular FPGA wants, whatever the hard IP core wants, to this this kind of format. Now, I'm not using exactly what the interface is on the P-Tile. These are the same, but some of the sideband signals are a little bit different. But by making it the same as the P-Tile, you get the performance advantages on the P-Tile. You know, it's very easy to port to the P-Tile, and it's actually pretty easy to adapt to this setup on the other FPGAs. So that's kind of the direction I'm going in there. I have the DMA engine with the new interface working. I've tested that in the hardware. I need to convert kind of the register interface side of things, and then I need to write all the muxing and demuxing logic And there's also a bunch of flow control stuff that I need to figure out, right? Because with the Xilinx devices, with the separate interfaces, the flow control is a little bit less important, because if one of them blocks, then the other one's fine. At least in terms of data flowing from the PCI Express IP core into the FPGA. But going the other way, it's a slightly different story. So yeah, I'm working on the models for the various Intel FPGAs so that I can actually test this stuff, and then I'm working on porting the actual PCI Express Verilog code. Not there yet, but hopefully within the next, well, I don't want to give a time frame on this because I got a lot of balls in the air, if you will. But eventually, in the near future, I'm going to have Corundum running on both of these Stratix 10 boards, and as part of that, I'm going to have all the PCI Express stuff sorted out. Actually, one thing that I was blocked on for a while is implementing a bunch of kind of transaction layer stuff in the PCI Express simulation framework. So one thing that happens in PCI Express is there is a TLP ACK-NAC protocol that controls how the TLPs traverse the links. So I had to implement a portion of that along with the exchanging of the link layer traffic as part of that. And then more importantly, there's a bunch of flow control credits that PCI Express uses to control the flow of TLPs over the links. And that was probably the more important thing that I had to implement. So I sat down and implemented that. I think all that is operational at the moment. There are actually some pretty major differences in terms of how the flow control credits are exposed between these cores. So there's still a number of things that I'm still working on sorting out in terms of minor interfacing details. But hopefully, once I get all that sorted out, then I'll be able to get that thing operational. Okay, it looks like actually the Stratix 10 DX is just about done here. So if the MX is not going to cooperate, we'll see about that. Maybe it will. We can at least take a look at the code on the DX. Let me go ahead and get the board swapped out again. Okay, now I just need to wait for the generate programming file to complete, and then we'll see if this works. You got one of these non-linear progress bars. It's been stuck at 4% for like a minute. That's annoying. But yeah, as far as the PCI Express stuff, I may do another stream on that at some point. We'll see. I'm not sure. That can get pretty technical. Taking this thing so long. 2 minutes and counting. Oh, okay. Now it's doing something. I have to wait for it. Oh, it says it was... Oh. Classic. All right, let me go ahead and hit start here. Gonna work. Oh boy. What is my OS? I'm running Arch Linux with XFCE. And I found a combination of themes that I kind of like. Relatively simple. Let's see. How did I set this up? So I have appearance. I installed 2 different themes. I think I have Graybird and I have Blackbird. So Graybird is for the Windows, and then the other one. I think that's under Window Manager. Yeah, okay, that's what I did. So I did Graybird for the main UI components, and then Blackbird for the borders. So I think it looks nice. That's kind of the default setup that I put up on all of my computers. So, okay, let's see. We'll hit start here. All right, where was my... Hey, it came up that time. Let me see here. Woohoo, it works that time. All right, so we didn't have to do anything because the state machine that we plugged in there wrote to the necessary registers in the P tile and configured everything correctly. So there we go. Next step, I got to get this thing working at 25G, and I got to get this thing working at 100G. So I'm not going to do that right now. That's going to take a while. All right, let me put that. All right, so now the question is, that's probably going to take at least another 10 minutes for that guy to finish. The annoying thing about Fortis Prime is that it's supposed to have some sort of an incremental compilation, at least in terms of when you add the signal tap components and whatnot. There is a button you can push for doing an incremental compile, but what I found is on these big chips, it really doesn't save you any time. Maybe it has something to do with the fact that the designs are so small. But yeah, that's I would just say that it's like it takes maybe half an hour or something to run the, to run the whole run all the way through, place and route, synthesis, place and route, everything. When you run the incremental one, it still takes like a half an hour. So it's like, well, I'm not really saving any time by doing that. And it's also ended up tripping me up a couple of times because with a design I was working on a while ago, I was having issues with timing closure on one particular output register that was, I think, driving the input of a DDR flip-flop or something like that. And in the initial run, I didn't have a placement constraint or a timing constraint for that. And it ended up placing it in a really stupid location. And then I was trying to get it to resynthesize the design and move the register, but it just wasn't cooperating. It's like, oh, I've already synthesized this. I've already placed it. I don't need to touch it. So I ended up having to delete the entire project. Fortunately, I had my makefile thing set up, so I deleted the entire project and regenerated it, and then it worked. I'm like, what the heck? There's not even I couldn't even find a way to like clear out the cache or something and force it to rebuild the project from scratch. So probably a button that I missed somewhere, but it's the incremental compile is not perfect, shall we say. All right, well, I'll just leave this up here. Hopefully that will finish up soon. What do I have here? I have some of that PCI Express code just to take a look at real quick. I'm working on that. This one. Yeah, I think it was this one. Yes. Was it? EMA-IF. Yeah, okay. Yeah, so this is, want some more details on the PCI Express stuff. This is the ultra-scale version here. Ultra-scale PCIe DMA interface. So this has just an AXI stream interface coming and going, basically. So this connects to the RC and RQ, and then the CC and CQ, you use different modules for that. Let's see. I guess I don't have a top level for this one yet. I just have the separate read and write modules. But this is the interface that I've been working on for the generic module. So the way this works is we have the TLP data, and we have the header. And I guess I don't have the TLP prefix at the moment. I have not done anything with those. At some point, maybe it would make sense to add that. But yeah, by pulling these out on separate signals and then adding the start of packet, end of packet, and whatnot, it's we're getting to a point to where this more closely matches the what the P-tile interface looks like. So I don't have a wrapper for that one. Well, I guess this is the one I was working at that actually does the adaptation between the two. Right. So this one has the TLP input and output for the read module here, right? So we got TLP in on the read. So the read module, it's going to issue read requests, and then it's going to accept the completion TLPs here. So that takes, data and header. And then I have the write module here. This is going to be generating write requests. That's what comes out there. And then the code that I have up here is necessary for just taking that information and packing it into the kind of the ultra scale TLP headers, or the ultra, whatever they call it. They call it the read and write descriptors. Requester, request, descriptor. Yeah. Oops. Yeah. So that's what this is set up for. It's not particularly complicated logic. And the other nice thing about separating this is it makes actually this core logic much simpler. And this is 1300 lines, right? This is the updated one. The previous one for ultrascale is 1700 lines. So yeah, you save a fair number of lines by making the more generic interface and by peeling off kind of the device specific interface code. One thing that I'm scratching my head over right now is resource consumption. It's similar, but I think it's about 1,000 registers, 1,000 flip-flops higher. And I haven't figured out exactly where that's coming from. That's basically 2 register slices across the 512-bit interface. So in principle, not that big of a deal, but 1,000 registers is 1,000 registers. So, but the flip side, if it does make the code more generic and more portable, then it's a significant advantage. One of the main advantages of this particular setup is I can use the same kind of PCI Express DMA core logic across all of the different targets, and I don't need to basically make a DMA module for each FPGA. That was how I was originally planning on doing it, but after I came up with this idea, I'm definitely not going to do that, because that's just going to create a huge amount of annoyance. Yeah, let's see. I have been working on the P-tile model here. This is code that's in progress. Yeah, so this is, let's see, this has the P-tile. Oh, so this is for the kind of split interfaces for the P-tile. So this one is responsible for generating the header and outputting it on a separate interface and whatnot. So the core of this is actually not particularly complicated. So this generates all the data, pulls out the header, pulls out the prefix. This also handles the parity. Actually, the one thing I'm not sure about that I'm gonna have to sort out at some point, although maybe not, I'm not using parity. I'm not sure if they'd use even parity or odd parity. It's a question of basically whether it's inverted, and I have not been able to make that determination by looking at the manual. Yeah. Let me just put it this way. The Xilinx documentation, while not great, is way better than the Intel documentation. Yeah. Although there is definitely a lot of variance in the Xilinx documentation. Some of it leaves a lot to be desired. Yeah, there are some interesting design differences as well between some of the modules. Like the P-tile, it has a bunch of kind of TDMA interfaces. So instead of providing a whole bunch of interfaces in parallel, it provides, so this kind of configuration output logic, it has one signal for the current function, it has one signal for kind of an address, and then it has, I think this is like a 16-bit configuration output. And then it cycles through a whole bunch of different values. And the idea is you can look at the address and then latch in whatever value that you're looking for. So the advantage is it doesn't use very many pins. The disadvantage is, well, that you might have to wait a while to get some of these values. But the idea is most of these don't change very often, right? Software might turn something on or turn something off. So if it takes a handful of clock cycles to update it, it's not really that big of a deal. But on the Xilinx IP core, they tend to provide a lot more stuff just directly on signals. So that does make it a little bit more complicated to interface with, because you have to write a little bit of additional logic to peel off some of the fields that you need, like the max read request and the max payload size. But it's only a handful of lines of verilog. To be honest, it probably makes a bigger difference just in terms of building the verification components, because you need a little bit of additional logic here. Like, this is the other end of it that extracts the information from that interface for the MSI address and the payload size and read request size and whatnot. So, there is one other major annoyance. I don't know exactly the best way to describe it about the P tile. I don't know why they designed it this way. But they have it's very common to have like a bar hit signal that indicates which bar the read request or write request is targeting. And they have a single result, or they have a single value for IO bar. It doesn't tell you which bar it is, it just says, oh, you hit on IO bar. I mean, I guess who uses IO bars at this point, so is it really all that big of a deal? But it would be nice if either they didn't differentiate between IO and memory bars, and they just said bar 0 through 5, which would be good, or if they actually told you what IO bar you were hitting. So it would just be one more bit, but apparently that's too complicated. Yeah, so I actually have not implemented that little section yet, because well, I guess in my test bench I only have one IO bar, so instead of reading the bar hit to figure out what bar, just if I got an IO request, there's only one IO bar it could have hit. Otherwise you have to do all that manually, and I don't think, I mean, how do you even get the base address register settings out of the core? I'm not sure how you do that on the Intel core, because usually you just use the bar hit to figure out what bar it was. Yeah, because I think all of the sideband signals that are output here, all these configuration signals, this doesn't actually include any of the bar configuration. This is mainly just a bunch of capabilities, fields from various capabilities. So interesting. Well, I'm not using any IO. I'm not planning on using IO, so it shouldn't be that big of a deal. Okay, it's almost done. This is running the running the fitter. 27 minutes. All right. Hopefully only a couple more minutes, and then we'll be able to test the MX. If it works, it works. Hope it works. Okay, anything else interesting to show here? Yeah, in terms of the PCI Express stuff, I recently made a release that included a huge list of changes, mainly covering kind of the link layer stuff. So this DLLP file I have here, this is only a small part of it. This is for the actual packets, but a large part of the change was all the stuff in the port module in terms of handling the DLLPs and handling the flow control as it's threaded through some of the other components. At some point, what I want to be able to do is implement the PCI Express pipe interface, although there is kind of some question as to exactly how that's going to be integrated with the rest of the setup. I'm not sure if it makes sense to, replace one of the port modules or make something that can be connected with one of the existing port modules. That I need to implement a lot more of the stack. But if I implement the pipe interface, then that means you would be able to use this stack with a commercial PCI Express IP core, or with the actual models that Xilinx and Intel provide for their IP cores, because all those are simulated with a host interface of with the pipe interface. So at some point I will circle back and get that working. couple of asserts here. Why those are commented out. Whatever. All right. Doing the timing analysis. Nope, it's running the assembler. Oh, very good. All right, so this is almost done. All right. A couple more minutes, and then we'll be able to do a quick test and hopefully be able to take a look at what's going on at the physical layer. Maybe it'll actually work this time. Play. Okay, but while this is finishing up, I'm going to swap the boards back one last time. All right, the MX board is running again, so give this a couple more minutes. I think this is just about done. We have yet another one of these non-linear progress bars. Stuck at 4% until it's done. Great. What's the point of having a progress bar in that case? Okay, nice. Looks like that finished. So, as soon as this decides to get itself figured out, go ahead and load that up. Okay, go ahead and program that. Where was the... Oh, hey, link came up that time. All right. Nope. Have a link, but there's still something wrong. All right, well, we tried. I'm not going to run this again today. Oh, what? Oh, man. Okay, that's fine. Yeah, it looks like it's still not, it's still having trouble getting block lock. Dang, I don't know what the heck happened. All right, well, at least we got the DX working. I don't know what the deal is with the MX. And I don't think you guys want to watch Cordis run for another half an hour, so I think I'm just going to call it at that. If there's any other questions or anything, go ahead and ask. Otherwise, I think I'll call it a day. Well, I will take a quick look, see if there was anything obvious that I screwed up on. I did replace the IP file. Didn't regenerate it though. Yeah, maybe that's the issue. Could still be a transceiver configuration problem. Oh well, not going to do that today. All right. Yeah. Let's see. I'll close all this stuff down then. All right. Well, if there aren't any questions, then I guess I will go ahead and finish off the stream for today. Thank you everybody for tuning in.